Yep, okay. So this is a bit you've got problems with. Okay. Now remember we said just before this that we have our normal erection system. So when the gyro starts to topple or precess away from the vertical, these electrolytic switches, the supply will cause it to precess to keep it back to vertical. Okay? Agree with that?
Okay, agreed.
Yeah, so it keeps the axis vertical to the Earth's surface.
Okay.
But now, if I take a very steep bank, okay, usually go like that, quite steep, or I slip quite a lot, you can see if I take a steep bank or I have centrifugal force, it could cause the electrolyte to complete a circuit. Okay?
Okay.
It was electrolyte and it would start to precess. But during a turn, a bank turn, even though the gyro is vertical, okay, even though the gyro is vertical, it's now being precessed away from the vertical axis. So you've got the force causing it to precess, but at the same time, that force acts on. So basically, I've got an error in roll, okay? There's my roll torque motor that's on the pitch axis, but as I'm precessing there, it also puts a torque force because of what's happening in this bank turn onto the pitch axis, which causes the pitch roll motor to precess. So now when I come out of a bank turn, this erection system will cause the error it had in roll because of a large bank or centrifugal force to transfer. So it'll transfer from roll into pitch when you come out in straight level flight. Okay, so just remember that during a bank turn, if we don't do anything, roll will transfer into an error in pitch. So what we do to avoid that, remember the gyro is got rigidity, so always wants to in the short term, it always wants to point in the same direction in space. So in the short term, that shouldn't move. So what we do, so this error in roll can become an error in pitch. But what we do, if you actually look here, we do something called roll erection cutout. And if you actually look at the switch, okay, here's what normally happens. You complete the circuit, the torque motor will move. But if I have excessive bank, very steep bank, or I have high levels of centrifugal force, you can see that the electrolytic switch, the electrolyte all goes to one end. And if it all goes to one end, the voltage, it can't go anywhere. So therefore, the erection torque motors don't work. So in accelerations greater than 0.18 G for centrifugal force, or angles greater than 10%, we take out this leveling system, this roll erection system. So therefore, we can't precess the gyro during a turn. Therefore, we can't get an error in roll. Therefore, we can't get an error in pitch when we level out.
Okay, Ian. Thank you.
Anyone else? Any questions? Okay. We're all good. Right. So we've worked out, so we now know that our compass systems, okay, we've got the actual compass heading, we have a true compass heading, and we have the magnetic compass heading. And the differences between the two, the difference between the magnetic north, the magnetic heading of my compass and my true compass heading is variation, magnetic and true. The angle is variation. When we look at the compass, what the aircraft compass is reading, but what it should be actually reading, the magnetic heading, we call that deviation. And the deviation is caused by the magnetic fields caused by the aircraft's own structure, gearboxes, frames, etc. Variation, we can take out variation, we can use maps. Electronically, we can actually take it out if we know where it is in the Earth. Deviation is slightly different, okay? Deviation is slightly different. We physically will have to do something to the compass to get rid of it, okay? And how we do it, those who have actually done one, we're going to do a compass swing. This will take out this or reduce this error to as low as possible. Has anyone ever actually done a compass swing on an aircraft? Helicopter? Anyone? No? Right, so we're going to look at what these errors or what this deviation is going to do to my aircraft. Not only what it's going to do, but when it's going to do it. Okay, so that's what we'll look at next. And get this to work properly. Right, hopefully that's now going to work. Right, so what we're going to do is look at what the aircraft's own magnetism does onto its compass, okay? And what we do is we actually look at how the aircraft's magnetic structure affects the compass in three axes. The longitudinal axis, so down the centre of the aircraft, across it, which is the lateral axis, and the vertical axis, okay? And the vertical axis. And yet again, it actually has values, okay? Yet again, it has values. It's got positive and negative. And we call these the magnetic components, okay? We call this the magnetic components of the aircraft structure. And these is what provides the errors in the aircraft compass system. Let's try and make life easier for us, okay? As you can see there, the P component is down the aircraft's lateral, okay? So that's the forward of the aircraft, that's the longitudinal axis of the aircraft. The Q component, again, is across the lateral, i.e. the wings, okay? Across the wings. And R is the vertical component, okay? R is the vertical component. So let's start with making life easy for ourselves. I'm going to tell you now the vertical component, the R component of the aircraft's own magnetic structure, we can ignore in straight and level flight only. Okay? We can ignore it in straight and level flight only. Let's look why. Here is a picture I drew early. So now if you see here, there's my R component. Okay, there's my R component, the vertical component. And as you see now, it's straight through the aircraft vertically. And if you look here, here's my compass. And when the aircraft is in straight and level flight, the R component is acting vertically down the whole aircraft structure. So what I can actually say is, there's my little compass. I can actually say that the R component operating on the white part of the needle is the exact same component is acting on the red part or the north part of the needle. So can we say now, looking at that diagram, that in straight and level flight, the R component has no effect on the compass needle? Yeah, you all agree with that? Yep. Now let's look at the aircraft when it starts to go nose down or nose up. It's no longer in straight and level flight. But what I can actually say now, that would still be vertical, the R component. But what I can see now is it's going to affect, on this, as it's going down, it will affect the white needle, or white part of the needle, more than the red part. So it would actually try to pull the needle down. So my compass will have an error. Okay, my compass will have an error. Okay, there's not a lot we can do about it, believe it or not, when the aircraft goes up and down. We just have to accept it. So, gentlemen, in straight and level flight, we can ignore the R component. Yep. So please remember that, gentlemen. What part of the aircraft's magnetic structure can we ignore in straight and level flight? It's the vertical or the R component of the aircraft's own magnetic structure. Job done. That's it. That's all you need to know about R.
Sir,
now, yes.
can you repeat the last sentence again?
Okay. What we can see is, in straight and level flight, we can ignore the effect that the R component has on the aircraft's own magnetic structure. We can ignore it, okay? Only in straight and level flight. When it's climbing and descending, there's not a lot, in this particular case, we can do about it, okay? So R, that's that done. We've done R. We don't have to think too much more about it. But now we've got P and Q. And depending how strong, you can see, I could basically say, I could call that, and have my little pad. I could say, I call that a north, that a south, that a north, that a south. And combined with the aircraft's, that's the aircraft's magnetic structure. Also, remember the compass needle always wants to go to magnetic north. So if I could actually say here, gents, if my compass actually Okay, that's my north needle. Going back to our laws of magnetism, like poles repel, unlike poles attract. Could I actually say, looking at this diagram, that the north side of the aircraft, the P component, is going to push this needle away, and this is going to attract it? Would you agree with that? So now, even though my compass wants to point to magnetic north, it's actually going to be repelled and attracted by the magnetism of the aircraft's own structure. And that can have problems for us, okay? Because now we're actually saying is, even we say that the aircraft, its compass is giving one heading, but actually, when we look at the magnetic north, the heading it should be on, it's not correct. So we need to be able to evaluate that, work it out, and we'll look at how we do. Well, we'll talk about that. So we can see now that the compass needle is going to be pulled away from where it should be heading, magnetic north. So let's look at how the aircraft's own magnetic structure affects. Now this is an ideal, okay, ideal view of how it works. Let's assume, okay, and we're looking at, and we said here, the P component was at the forward part of the aircraft. So now we can actually say, if I'm going to be more specific, the P component, the positive P component, there we go, right at the front. So we're just looking at how the longitudinal component, the P component, affects my compass. There's the aircraft flying to magnetic north. Here's my lines of the Earth's magnetic field. So now let's look at it. The aircraft's magnetic structure, okay, is positive, for the P component is positive here, this red point. So you can now say my aircraft compass wants to point to magnetic north. But also the aircraft magnetic structure is also in line with magnetic north. I've got the two magnetic effects acting on my compass needle are the magnetic north and the P component, and they're both in line. So can I say both will pull the needle to line up with magnetic north? Yep. And if we look at the graph, there is zero deviation. Yep. The magnetic needle lines up with magnetic north, and it lines up with the P component of the aircraft structure. Therefore, my needle is actually flying, is actually pointing to magnetic north. I'm now going to turn the aircraft round 90 degrees, okay? I'm going to turn the aircraft round 90 degrees. Again, there's still magnetic north. My compass needle wants to line up with magnetic north. But now, the P component, okay, the positive part, is still at the front of the aircraft. My compass needle wants to line off magnetic north, but it's getting pulled by the P component of the aircraft structure. So now you can actually see now it wants to line up with magnetic north, but here is the force, the attraction force caused by the P component, and there's my resultant. Yeah. And what we can see is the P component, its effects on the compass are maximum when the aircraft is flying at 90 degrees. So we've got maximum deviation. We fly around to 180 degrees again. There's our component there. But it's causing us to line up. So actually, my P component is just making my line up again with the aircraft structure. So I can actually say, when I'm going south, there is zero deviation caused by the aircraft's own magnetic structure. Let's look at west, 270 degrees. Again, there's the P component, the positive P component. There's magnetic north. So basically my compass again wants to line up with magnetic north. But I've also got the force caused by the P component pulling the needle away from magnetic north. So now I have a resultant compass needle heading like that. So what I can actually see again is when the aircraft, with the P component, when the aircraft is flying west, there is maximum deviation away from magnetic north. Okay, and when I come back round to north again, we're starting there. So what we need to think about is, what does that do to our compass? So the P component has maximum deviation when the aircraft is flying west. So basically, the P component causes the aircraft to move away magnetic north, and the maximum error is when the aircraft is flying east and west. Okay, so how do we remember that? Well, we have this little word, pew. P component has maximum deviation on the aircraft's compass when it's heading east-west. So if you can remember that, pew. The P component will have maximum deviation on the aircraft's compass system when it's heading east and west. Okay? Are we all happy with that understanding? Does anyone want me to go through it again? No, we all happy? Good. Now let's look at this, the Q component. Okay, the Q component. And if we go all the way back here, Q is across the wings, okay, the lateral axis. So Q affects the aircraft, the compass, with the magnetic fields in the lateral axis, i.e. across the wings. So So we can see now here, there is our so again, here's my Q component going across the wings. Yeah. And again, here's my magnetic north. And there's my lines of the Earth's magnetic field. So now let's look at how the Q component affects the compass. So basically, with the magnetic field across the lateral axis, let's see how it affects the compass needle. So let's start again when the aircraft is flying north. The compass needle again wants to line up with magnetic north. Yep. So it wants to line up with magnetic north. But now we've got the magnetic structure of the Q component. Again, it's on the wing. And it's pulling the compass needle away from magnetic north. So I now have a resultant compass needle like that. Again, so what I can actually say is, when the aircraft is heading north, the Q component of the aircraft structure will have maximum deviation when the aircraft is flying north. Let's look at the aircraft now. We turn it onto an easterly heading. Now look at the compass. It wants to line up with magnetic north. But now the Q component is straight down across the wings. So that also lines up with magnetic north. So what I can actually say is, my deviation of my compass is 0 degrees when the aircraft is flying east. Let's now go to south. Let's go to south. Again, my compass needle wants to line up with magnetic north. But because of this Q component, again, it's pulling it away from magnetic north. And there's my resultant. Okay? There's my resultant heading, or what my compass is showing. So what I can again say is, my compass deviates from its magnetic heading maximum, but in the opposite direction, when I'm going south. Yeah, maximum when I'm going south. Let's fly round to west. Now you can see, again, there's my Q component. It also lines up with magnetic north. Both are lined up, and therefore I can say the actual compass heading, what the compass is reading, and magnetic north, the magnetic heading, are exactly the same. So I've got 0 deviation. And again, I can fly back to north. Okay. So what I can say here is Q component causes maximum deviation of the compass when the aircraft is flying north-south. And if you look here, gentlemen, without any other problems on the aircraft, Q component would give us, ideally, a cosine deviation indication. And if you look at the P component, that must be a sine. There's a lot of mathematics in this, but we're not going to, luckily, we're not going to bother in this. So, what do we need to take out of that? Well, the first thing we need to take out of that, gentlemen, is you have to be able to understand where a particular component has effect on the compass system. Okay? P component will have maximum effect on maximum deviation when the aircraft is flying east and west. And that's the little word we use to remember it is P. Okay? P component, maximum east-west. Okay? P component has maximum effect or maximum deviation when the aircraft is flying east-west. Q component, okay, will have maximum effect on the aircraft structure when the aircraft is flying north or south, okay? Q component, maximum flying north or south. And this will put an error into our compass system. And we're going to look at how we get rid of that, okay, later on, okay? Well, in fact, I'll tell you, that's when we do a compass swing, okay? And what we'll actually do, we'll look at how we do that later on, but we're going to do a compass swing to find out this deviation, and then artificially, we are going to take out that deviation in our compass, okay? Artificially, we're going to take out that deviation in our compass. So, what have we learned so far this morning that we need to remember? The aircraft's magnetic structure, it can be felt in three ways: the longitudinal axis, the lateral axis, and the vertical axis. The longitudinal axis, we call that component P. The lateral axis, we call that component Q. And the vertical axis, we can call that R. And they all have a positive number or a negative number. P is always forward, Q is always to the right, and R is always positive downwards. As I've explained, which of the three aircraft's magnetic components can we ignore, but only in straight and level flight? It is component A, the vertical component we can ignore in straight and level flight. How does the Q component affect the compass? Sorry, how does the P component affect the compass? It affects it by having maximum deviation when the aircraft is flying east-west. So my compass is most inaccurate for the P component when it's flying east-west. The Q component will have maximum deviation or maximum error when the aircraft is flying north-south. Okay? So as we can see here, the Q component we can normally ignore in straight and level flight. Please remember that. Okay, and how do we get rid of this deviation or this error? We do the compass swing. Okay, those who've ever seen it, you'll actually have a little compass card, compass correction card. And if I have a deviation of +2 on a particular heading, which basically means it's overreading by 2 degrees, therefore to fly in the correct heading, I would have to take off 2 degrees. Okay? So let's have this quick look at here. This particular one, if I was flying to fly north 000, it says I have to fly 001. I have to fly one over. Why is that? Because basically it must be reading, its deviation must be -1. So to fly the correct heading, I must fly by +1. 30 degrees, okay, to fly at 030, it says I must fly at 029, which is 1 under, which basically means my deviation caused by my aircraft's magnetic structure means I must be +1. My aircraft is overreading by 1, so to fly on the correct heading, I must fly 1 degree lower. And that's what the pilot does, okay? And for those who have actually seen the standby compass, have you all seen the little corrector card somewhere by the standby compass? Yep? No?
Yes, we have seen.
Yeah.
So, and this compass swing, okay, gets rid of the deviation. And we'll have a little look at that this morning, how we artificially get rid of it, okay? How we artificially get rid of this deviation. Yep. Okay, it's 10:05. We'll go for a 15-minute break, okay? And then we'll come back and we will start again, okay? Any questions on deviation and the components of the aircraft's magnetic structure and how it affects the compass? Nope. Okay, we'll go for a 15-minute break and we'll come back and we'll get on. Make sure you get a good stretch. Okay, let's go. A good stretch. I'll see you in 50 minutes.
Okay.
Morning, gentlemen, again.
Good morning.
Morning. Oh, I know it's a Monday morning. Now you feel Monday, worst day of the week. Just let you know, when I came into my room to start doing some teaching this morning, 9 o'clock, outside, nice blue sky, sun, no snow. I've just come back from a break. We have over 2 centimetres snows fallen in the last hour. That was a weird weather forecast. We're forecasting all this week, quite heavy snow all week. I think I'll be outside with a shovel at lunchtime.
Which shovel?
No, shovel, spade, clearing the snow.
It's on over your house rooftop?
No, we're on the path to getting it. Yeah.
Very cold. So.
Yeah, when was the last time it snowed in Catman?
It's nearly more than
in 2006.
Yeah. I think that's the thing. A lot of people in the UK and Europe, when we all, until I've actually been there, you think about, only thing you think about when you talk about Nepal is up in the mountains, Everest, where it's always snow. So it wasn't until I got there I went, oh, that's very warm. Yeah. Because the last time we were doing the course, we were doing it starting at 6 in the morning. And of course, the other students were coming in with the big parka jackets, and there I'm with my light fleece, because I was used to the cold, and I'm built to survive in the Arctic. Okay, right. So, any questions on deviation and the effects of the aircraft's own magnetism has on its compass? Yes.
In this slide, compass correction. Compass.
Yep.
So we consider P component or Q component in this example.
Both. Okay. We talked about them individually.
Yeah.
But you can now understand. Oops. Depending on the aircraft's heading, depend which component has most effect on the aircraft. Okay? Yep, so P always maximum when it's going east-west, P is maximum north-south. Now this is an ideal scenario, okay? This is literally if everything was ideal. But in reality, gentlemen, you're going to have generators, you're going to have wiring all around the aircraft, which is going to have effects on the compass as well, okay? And this is why we do a compass swing, usually between 12 and 18 months. Now, some of you are going to say, we've got laser ring gyros. Yes, you have. But the standby compass, okay, a little standby compass, again, has to be calibrated every 12 to 18 months. Have you got a compass base at Kathmandu Airport? Does anyone know? No? Oh well, okay. Remember, we can ignore in straight and level flight, and if it climbs in descent, there isn't actually a lot we can do about it, because it will actually change with increase and decrease of the rate of climb. Okay, so that's the basic theory about it. But now we'll look at the direct reading compass, the standby or the emergency compass. Okay, just like the one I've got here. Okay, there's several types, but they basically all work on the same principle. Okay, they all work on the same principle. So we're now going to look at the construction, okay, and how a standby or emergency, or this basically direct, what we call the direct reading compass, has on the aircraft, or on the direct reading compass. So let's look at a few definitions, okay? Moment, okay? These are some definitions you will probably need to remember, okay? Moment, and it says there's the tendency to be turned by a magnet. So basically, if I have my compass, it's got a bit of metal, and if you actually look at it, okay, hold on, let me take out the background again, that'll work. So you can see my compass. You see that? If I bring, okay, you see that? How it moves? Yeah. So basically, the moment is the tendency to be turned by a magnet, okay? And what you can actually say is, there's two ways this moment can be increased. If the strength of the magnet is increased, it will start to pull the needle away from north when it's far away. If it's a small magnet, I need to get it closer. Okay? Need to get it closer. So that's the first one. So remember that definition, ladies and gentlemen. The next bit is basically, it says, the period is the time taken to go from one extreme to another. Okay. Best way to think about that is the pendulum on an old type clock. It swings. Okay. And the time to go from there to there and back again, that is what we call the period. Okay. And what does this period depend on? When we're talking about magnets, the first one is the mass, the weight of this pendulum, because then therefore gravity and momentum will determine how fast it comes down, therefore the shorter period. The next thing is the strength of the magnet attracting it or repelling it. Okay, if I've got a strong magnetic field, it's going to pull it quick. If I've got a weak magnetic field, it's going to pull it slowly. Okay, so remember those two definitions. Okay, magnetic moment is the ability to be turned or moved by another magnet. Period is the time to go from one place to the next end. Okay, so time to go from there to there. What does that depend on? The mass and the strength of that magnetic field. So let's look at the reading compass itself. It says it's totally self-contained. It doesn't need any air, it doesn't need any external power. The only time you might have it connected is for lighting, okay? But that has nothing to do with the operation of the direct reading compass itself, okay? It's only using magnetism. It's working just like that compass there. Where the compass rose, and that's what we talk about here, the compass rose wants to line up with north. Okay, wants to line up with north. And the next thing it says, it should be in the direct view of the crew or the pilots. Now, you'll find some aircraft out there that'll literally be down the centre of the aircraft. That'll always be in view. Those who are working on the A320s and the 737, I think you're all A320s, it's a little pop-up panel, and it'll drop down when required. That's correct, isn't it? You got a little panel. You push it and it'll drop, the compass will drop down, is that correct?
Yes.
And those who are in the helicopters, it's always in front of you, isn't it?
Yeah.
Yeah. So, either way, when it's required, it will be in the direct view of the pilot, okay? So, it's self-contained, doesn't need any power, except we need lighting. It's no different to what's on magnetism, so it'll line up with the Earth's magnetic field, and it must always be in direct view of the crew, and we'll look at why that's important in a minute. Okay. This is one of the ones here, this is called an E2 compass, okay? And there's different modifications of it. There's E2, A and B and C. This is an E2C, and all the reason I know that is, well, I took the photograph myself, but it has an electrical power lead for the lighting. In that little bit there's a little light. We'll look at that in a minute. This bit here is called the compass bowl. Okay, compass bowl. Again, it looks like that Mexican hat. Why do we have that sort of Mexican hat? Is to compensate for dip, because the compass bowl, the pivot point, where's my pen gone? My pivot point for this compass bowl is like this. So it's basically going up like this. Okay, so there's your pivot point there. And that bowl is below the rest of it. So it sort of goes down like this. Now, the next thing you're going to see is something, we'll look at this, but this is called the lubber line, okay? This is where the pilot will take his compass reading from, okay? The pilot will tell you it can take his compass reading from. These little triangles are little what's called adjustment screws, okay? Little adjustment screws. And that's what's going to compensate for my P and Q component. Now, I don't know if you can see there. This one here, this is the one. This is basically for my own, because I still have my own compass swing pack. The brass keys, okay, the key here, I've got one is made of brass, and another one is made of aluminium. They're non-magnetic. Okay, they are non-magnetic. So you can look here. I'll just hopefully hold that there. I'll hopefully steady. Come on, slow down. Now, if you actually watch, I'll put this here because it's brass. It's non-magnetic. It doesn't affect, hold on, it's still moving. As you can see here, it shouldn't affect my compass needle because it's non-magnetic. So never use magnetic tools near a direct reading compass. And what these little keys, okay, are connected to are little tiny little magnets in between 3 and 4 millimeters long. And I don't know if you want to see it, but if you actually look here, there's one of the little magnets, okay? You can see the little yellowy, that's a bit of brass, that's a brass cog. Don't know if you can see it. Here we go. You see the teeth on the cog?
Yeah.
Yeah. Well, that's actually, when you turn that little screw, that little triangular screw, that turns that cog. And that cog is attached to a tiny little bar magnet about 3 millimeters long. And what it does, it turns. And remember now, if I now go back to my deviation, okay, so what I would actually do on here, if I have a big deviation there, what I'm going to do is I'm going to turn my little bar magnet to try and bring back this deviation as close to zero as possible. So during the compass swing, I'll do some calculations. We don't have to do that on here. And it'll work out how many degrees I have to move my compass to hopefully get this deviation close to zero as possible. So that's what we're actually doing in the compass swing. We're going to adjust. Okay, we're going to adjust these, okay, to get rid of my, well, I know this one here is my P component and that one will be my C component. Yeah, I just accept that I know that. Okay, we're not going to go in the great depth. So there's where the pilot takes his reading. That's called the lubber line. Okay. That there is called the lubber line, and that's to stop the pilot getting what's called parallax error. The pilot must be directly in front of this line to get the reading. Because if he looks from this side, he'll be looking across it and he'll get a reading over here. If he reads from this side, he'll be getting a reading somewhere over here. So it has to be directly looking at that line there. Okay, has to be directly looking at that line. It must be able to operate at all angles because the aircraft can go up and down, roll right and left. And there we go, look at the bottom. Able to be corrected for external forces for my P component and my Q component. So let's have a little look at the internals of it. Okay, let's have a look at how it works internally. The clear part, okay, the clear part you can see there, that's a clear plastic bowl, okay, and inside that there is a silicon fluid, a clear silicon fluid. So the first thing is a plastic bowl, okay, thick plexiglass or clear plastic with a silicon fluid, okay. That silicon fluid is there to provide any dampening. So as the compass turns naturally, as soon as the aircraft stops, it was a nice gentle turn, it should just slightly overread and then come back. So the fluid is providing dampening and lubrication to this compass bowl, okay? And that there, you can see it there, that's your compass bowl. Okay, compass bowl. That's where all the writing is. So I'm going to have on here so that'll be like south, east, okay, north, 010, 045, etc. So that's where that writing is, okay? So the compass bowl That's where the writing is on the compass bowl. So this silicon fluid prevents dampening. We're going to look at what also that silicon fluid does. It has a positive thing on it has a positive effect on the compass, but it also, in certain conditions, can have a negative effect on the compass. There's your pivot, okay? There's your pivot up there. You can see there's most of the compass bowl is actually below the pivot point. Therefore, we're reducing the effect that dip has on the compass. Therefore, we hopefully can go further north, okay, by approximately 3 degrees. And then we have a little light, so you can see it at night, okay. Now, just be careful, gentlemen, if you ever have to go and change the little filament or little light bulb in there, the base or the metal part of the filament is made of brass, okay. It's just a normal little P lamp, but the base is made of brass, therefore it's non-magnetic. So please don't put a normal steel-based P lamp in there, or it will cause the compass to be inaccurate, because the steel is magnetic. Then at the back here we have these what's called liquid expansion capsules. Okay, liquid expansion capsule. Now, gentlemen, most of you are all mechanical, okay, either 1.1 or 1.3. And you all know now, if you've got fluid, you can have cavitation, or you've got your bubbles. Yes, like in hydraulics, it won't work correctly. The same on here. If you get air bubbles in this plastic bowl, you'll have problems. But also, let's look at why we have these expansion capsules. Okay. Imagine I am, let's say I'm in Dubai in summer, okay? And we said that the compass is sitting in the front of the window of the cockpit. You've all been in a cockpit in summer with the sun out, it gets very, very hot, doesn't it? Even though outside it might be only 20, 25 degrees, in the cockpit it can easily get 30, 40, 50 degrees centigrade. When liquids start to heat up, they expand. And if that was a fixed volume, this liquid would find the best way to get out, either to cause a crack in the plastic, or any of the seals, okay, or joins, it would try and force its way out and leak. So what happens is this fluid starts to expand, it goes into these expansion capsules and they fill up with the fluid. So we don't get too much pressure in that liquid bowl. But in the other direction, when it gets cold, okay, when it gets cold, the fluid contracts, okay, the rubber also contracts and it pushes the fluid in here, so you always get the compass bowl full with fluid, therefore no air bubbles. So a couple of things in there we're going to look at is, why do we have the lubber line? It basically gives the pilot the direction he's be flying. The liquid, okay, we've got liquid in the bowl, it provides dampening, and we'll look at another problem it causes later on. But why do we have the expansion capsules? Okay, basically to take up the expansion of the fluid, okay, or the contraction of the fluid due to temperature. Now, we're going to look at some errors, okay, some errors we have in the compass system, okay, and we break them down into two main parts: mechanical and dynamic. Okay, mechanical, they're there because it is a mechanical device. Dynamic happens when there is movement. Okay, dynamic happens when there is movement. So let's look at these individually. The first one is called pivot friction. There's a pivot. Okay, it's supposed to be called what's called a dual cup. It's a low friction pivot. I can't think of another word. Oh. It's a low friction pivot. Now over time that pivot might get worn. And it's one of the first things when you go to do a compass thing or do a function on the compass, it's one of the first things they tell you to go and check. Okay?
Hello.
टेक्निकल भएको हो
Oh, हरायो इन
गयो
त्यसो भए हाम्रो प्रब्लम हो भने उतैको प्रब्लम हो ल भयो
So what we're going to do is we're going to carry out a pivot. So first thing we do, we note the heading.
इन वी क्यानट लिसन यु इट्स टेक्निकल
Hello, Wayne. सुनिरहेछ अरूलाई
सबैले सुनिरहेछ इन बाहेक
हामीले त सुनेछ
कहाँ गयो यार
कन्भर्सेसन
एकले बोले होला फेरि
उतैबाट प्रब्लम भयो जस्तो छ
धेरै स्नोइङ भयो जस्तो छ कम्पास भित्र
Do you hear me, gentlemen?
यस
नाउ
we can hear sir you start from the pivot friction now
I'll just try and hopefully show you again. I need to get the picture up. Can you see the compass? Yeah?
No.
You see it?
No.
Yeah.
या
Right. And what we actually do is a bit difficult because I've got it at an angle. Okay, can you see the compass needle here?
नॉट क्लियरली मेक इट अप अ बिट
But what I'm going to do, you see how it
Can you-
moves?
can you repeat pivot errors again from pivot friction
Right. So So what I'm going to look at the pivot friction. What I want to do, okay, I'll just probably have to talk through it, because I can't really show, it's not coming up too well on the camera. What I'm going to do is I'm actually going to check the friction. There's no damage to the pivot. That's what I'm really looking at. There's no damage to the pivot on my compass. So what I'm going to do, okay, now the procedure is in your notes, okay, under pivot friction. So what I'm going to do is I'm going to, now it will say in your maintenance manual, it might say get a magnet or a magnetic object. Don't. Just get a screwdriver or a pair of pliers. That is magnetic enough. Because if you put a magnet too close to the standby compass, you can do what's called polarize it. It can actually basically flip 180 degrees. But what you do is you get a magnetic object, you bring it towards the compass. So what you do is you note the actual heading on the compass. In fact, hold on, I'll be able to do it with this. Okay, just let this slow down. Slow. Right. So what we do for pivot friction test is we note the heading we're on. I then get a bit of pair of pliers, something ferrous metal, and watch. I deflect it away from its heading. And I see if it comes back to the same heading. Yep, it has. And then in the other direction, I deflect it the other way. And again, see if it comes back to the same heading. And as long as it's plus or minus whatever it says in the maintenance manual, it's serviceable. Yep. So that's a pivot friction test. What you must never do during a pivot friction test is tap the computer. Tap the compass. Because if you tap it, you're getting rid of the friction. Okay? So, let's talk about pivot friction tests. Why do we do it? It's to check the accuracy of the compass, i.e. make sure that the pivot is good. Okay? How do we carry it out? We note the heading that the compass or the direct reading compass is indicating. We get a bit of ferrous metal and we move it towards the compass. The compass will deviate away. We take the ferrous metal away. The compass bowl should come back to the exact same heading. And then we do it from the other side. Deflect it away. Take the ferrous metal away. And we see if it comes back to the original heading. The one thing we should never do is tap the compass during a pivot friction test, okay? That's not just for any exam, that is for real life as well. So what must you never do during a pivot friction test is tap the compass. Okay, is tap the compass. So you all happy on how to carry out a pivot friction test? And we're all happy what we should never do during a pivot friction test. Yep, never tap it. Okay. The next one is called parallax error. Okay, parallax error. This is basically down to this lubber line again. Okay, this line here. As I said earlier, for the pilot to get a very accurate reading, he must be directly in line with that lubber line. If he's looking at that way, he's going to be seeing the number there. If he's looking from this side, he's going to be seeing the number there. So how do we get rid of parallax error? Is the only way you can do it is the pilot must line up directly behind the lubber line to get the correct and most accurate reading. Okay, the pilot must line up directly behind the lubber line to get the most accurate reading. That's the parallax error. Okay. Next, we're going to look at is something called liquid swirl error. Okay, liquid swirl error. Now, I did say 10 minutes ago, 15 minutes ago, that in that compass bowl we have a clear silicon fluid. Okay, clear silicon fluid. Years ago, that fluid used to be paraffin or kerosene. And for obvious reasons, we got rid of that. But we've got this liquid swirl. Now, I did say that the liquid in there has a positive, beg your pardon, okay, has a positive thing for the computer, I keep saying computer, for the compass. It provides that dampening. So any small vibrations, or as the compass slowly goes round to a heading, it stops it from flying off back round. But this fluid, okay, this liquid can also cause problems, okay? If I'm turning fast enough, okay, now hopefully now if you look at my compass, if I turn slowly, okay, it goes nice and slow, that's not a problem. Yeah, now what happens, I'm just going to let it rest. Let it rest. Now look what happens when I do it fast. See what's happening to the compass? Look at it. It's going well past 360 degrees. It's rotated over 360 degrees. Why is that? Well, if I move the fluid, if I move that bowl fast, the liquid also starts to turn. Even if I stop moving the compass, you can see the compass bowl is still turning. And that's because the liquid in my direct reading compass is continuing to turn. Okay, it's continuing to turn. So the first thing we can do is say liquid swirl, okay, is caused by the fluid.
Your video is off.
Pardon?
Your video is off. You can't
Is
see.
it?
Yes.
I've got it on. Can anyone else not see me?
No, we can see you.
Actually,
I
we
can
are not.
see you. Sometimes you are stuck.
No, it's like you have to pin to put him on the screen. If somebody is speaking, he's on the there, like I mean on the blue corner.
Yeah. Okay. Well, if you can't see me, count yourself lucky. You don't want to see this beautiful face too often. But as you can see there, liquid swirl, okay, as the liquid inside, you can see it, look, the liquid inside is causing the compass to continue to turn. So the aircraft could stop, but you can see there that the liquid swirl is caught hold of the compass rose, and it's caused it to continue to turn. Now that's an exaggeration. You're not going to find an aircraft going like that. Okay, the only time I think you can get an aircraft going like that is when a helicopter loses tail rotor. And I don't think he's worried about the compass then. So, liquid swirl, okay? The rotation of the fluid causes the compass needle, to what I can tell you now, even in commercial airliners, if the pilot does a very, very sharp, high-speed turn, his compass will become inaccurate. And remember what I said when we talked about turn and slip indicators? That we use that because at certain times the compass becomes inaccurate. This is it. So during turns, our compass, because of liquid swirl, that's one of the, can become inaccurate. And the one thing we can always say about liquid swirl, it adds to any type of error. We're going to look at another two errors later on. Well, next. So, the one thing we can say about liquid swirl, it will always add to any error. Okay, so if the aircraft moves, that liquid will start to turn and will cause it to continue to move. Okay, so remember that there. Okay, liquid swirl always adds to any error. Okay, and the next two errors we're going to talk about, it also has a big effect on. Okay, and the next two things we're going to talk about is northerly turning error and acceleration error. Yes, somebody who's been speaking.
Yeah, me. Yeah, one question that in which direction liquid swirl error?
Doesn't matter. If it went clockwise, it would keep the compass rose going clockwise. If it went anti-clockwise, it would keep it going anti-clockwise. So all you need to remember is liquid swirl always adds to any error. So let's say momentum of the compass starting to go clockwise, maybe wants it to overshoot by 3 or 4 degrees. But the liquid swirl will cause it to, if it's fast enough, will cause it to go maybe 10, 15 degrees more in the same direction. Okay, so this is all you remember about liquid swirl. Why do we have it? It's because during fast turns, the liquid will it's got momentum and will continue to move and causes the compass rose to turn. What else do we know? Is liquid swirl always adds to any other errors.
Okay, thank you, Mahesh.
Especially the two we're going to talk about now. Okay? Especially the two we're going to talk about now.
So,
Yes.
so how can we reduce this liquid swirl? By only maneuvering?
We can't.
Okay, we can.
No, we're going to talk about what the pilots might, well, I'll tell you what the pilots might do, okay? But this error and the other two errors we're going to talk about, the laws of physics, okay, the laws of the universe apply. We can't get rid of it. We just have to be able to compensate or decide how we can get rid of it. And remember what I said on Friday when we talked about the turn coordinator and the turn and slip indicator? Remember I said there's certain times when the compass is inaccurate. Well, the two things we're going to talk about next and liquid swirl can make the compass inaccurate. Okay, so during turns or certain types of turns, my compass becomes inaccurate. And that's why we had the turn coordinator and the turn and slip indicator. With the clock, with the stopwatch, if I know how many degrees I want to turn, I do a quick calculation. I know how many degrees I want to turn, therefore if I do a calculation I can work out how many seconds I need to do a particular rate turn. So we've done parallax error. There you go, there's parallax error. Make sure you're directly behind the object. So the next thing we're going to look at is something called northerly turning error. Okay, northerly turning error. Find my let me find my pens. Now, luckily, we all live in the northern hemisphere. Okay, and as our notes are written for the northern hemisphere, that's what we're really going to look at. Okay. Now, we're going to have a little look at what happens to a compass. Okay. Just let me draw this. North, south. So, you've got to have a little bit of understanding of how the direct reading compass works. Okay. Now I'm looking at this direct reading compass now, and I can see it reading just about north. Okay. It's reading north. So I'm actually looking at it, and my compass, so I'm looking at it now, right there, it was saying north. But my compass needle is that end that points to north. Yes.
I cannot see your presentation. Is it my problem or yours?
I think it must be your problem. Everyone else can see me, can't you, gents?
No.
Yes.
Yes, we can see you.
Most people can see me.
Only we see you, but there is no any slide.
Presentation, I mean to say, not you. Your presentation.
Wait, can you not see the presentation?
Yes.
Can anyone else see the presentation?
Yeah,
Your
I
presentation,
see the
also and your picture also.
Yeah.
No.
What I suggest you do, if you can't see me, or you can't see the presentation because everyone else can, go out and come back in again. Okay?
Okay, sir.
No presentation.
Do the avionics technician's #1 fault finding tool. Switch it off and switch it back on again. Oh, you beans all know that. How we doing now? Can you see the presentation now?
No.
No.
But everyone else can see it.
Yeah, it's a liquid swell, right? On your presentation?
Look, northerly turning error.
No.
Only we can see your face.
We are seeing only the liquid swell.
What does everyone else see?
Liquid swirl.
Liquid swell.
Liquid swirl. Oh, right.
Yeah.
Only liquid swirl.
Only the round.
Right. It's not. Okay. Let's have a look. What do you see now?
Liquid swell.
Same.
Liquid swell.
Same.
Right. Okay. For some reason, it's not changing picture. I'm seeing it's changing, but I can't. Hold on, let me try something. Discard. What have you got? What can you see now?
Dynamic
Dynamic
nursery
color.
turning.
Right. So you can, that's the one that should be on. Okay. So everyone can now see that. Good.
And no, me not.
Me also, I don't know, sir. I don't know. For me also, I can't see. I can see you only.
I am getting liquid seal.
Dynamic not be turning. Not be turning. I'm seeing the.
Who else can see dynamic northerly turning? Can you put your hands up, please, gents? Okay. Oh, put your hands down, please. Who can see liquid swirl? Right. Well, quite a few. And who can see nothing? Right, it's all different. I'm lost, Jim. What we try and do is
let's have 5-10 minutes break, then rejoin. That will be good.
okay. Is I'll take. Can someone? What I'll do is I'll come back out and I'll come back in again. Is anyone allowed to bring me back in again? I'll leave the meeting. I'll come back in again and see if that'll affect it. So go for a 10-minute break, okay? And I'll see if I can get myself back in again. Okay.
यादव सर के भइरहेछ यो
खै टेक्निकल एरर भइरहेछ
कहिले त्यस्तो
भइरहेछ
स्टक हुन्छ कहिले के यो स्वेयर लिएर के मात्र छ
Hello, how's that? You see me now?
Yes, we can see you.
Video.
Right, let's try that. What can you see now?
Yes, we can see the PowerPoint, dynamic northerly turning.
Okay, yeah. That's good. That's where I wanted to be. It's bizarre. It was three people were seeing three different things. That slide, the last slide, and nothing at all. Okay, so now hopefully now everyone's got that right. I'll just go for a quick break myself, and I will be there in 2 seconds. Hey.
ब्रेक हो जाए ब्रेक ब्रेक होता है नो वरीज हैन ऊ आफै गएर आयो कि हामी जानु पर्दैन ए आउनु भयो जोइन गर्नु भयो नि त अहिले ल जोइन गर्नु न त्यो स्तुबला त्यो के भन्छ सफ्ट कपी पठाउनु है त कहाँ इमेल गर्नु भएको छ त्यसमा ल्यान्डिङ गियर र फ्लाइट कन्ट्रोल मात्रै छ ए पछिबाट ए ल ल म हेर्छु के छ तपाईको इन्टरनेट स्लो भएको हो दाइ
अहिले मेरो सल्भ भयो है प्रब्लम
अहिले ठिकै छ हाम्रो पनि
शटडाउन गरेर फेरि अन गरेको के म
ठीक छ
Okay, we all back yet?
Okay, in.
Right, we're looking the two dynamic. It's basically caused by the aircraft moving, okay? So the first thing we got to know about northerly turning error, okay? Northerly turning error happens when the aircraft is going north. So that's the first thing. When does northerly turning error happen? The aircraft must be flying north. Now, if I actually look at the makeup of a compass, now if you look at it here, and my direct reading compass, even though I've said I'm looking at north, okay, so I'm actually looking at, there's north. But if you look here, there's the red north needle. Because remember, I'm actually looking at that direction. So even though in the compass rose, it says north, you can see at the opposite end, that must be the north pointing needle. So that's the first thing you got to remember. We're looking at it from behind the compass. So even though my compass rose, when I'm looking it says north, actually the north end of the compass ball is the opposite side. Next thing, what affects my direct reading compass? What force also affects my direct reading compass, apart from being at the equator? We have the effect of dip. Remember that? So dip's going to pull my needle, my north-facing needle, okay, down. Okay. So now, okay, I'm flying along. So I'm flying around north. And as it says there, I want to turn south. So basically, that's what my needle is my compass is now. It's getting pulled down towards the north. So now when I start to bank to the left, okay, or bank, it says there, to the west, what happens is I've got my normal dip. And as I now start to turn, okay, as I start to turn to the east, what it does is it pulls the needle down. The dip starts to pull the needle down. And if you can see here, okay, okay, if you can see here, now dip pulls the north-facing needle down, okay, and my compass starts to show a heading towards east, even though I'm turning west. Ooh, and that's all down to dip, okay? And if what is happening is, very difficult to show you in the computer, on the computer, but basically, it's tilted up. As I start to tilt, it basically pulls this round. Okay, so even though I was heading north, I'm turning west. The dip causes, with centrifugal force, causes the compass to turn towards east. Okay, causes it turn towards east, and this all happens due to dip. Okay, it's all down to dip. If we didn't have dip, the centrifugal forces wouldn't have much effect on it. Okay, so northerly turning error happens when the aircraft is flying north. So basically an arc either side of north. Okay, and as the aircraft turns east or west, okay, it says here the compass magnets were initially pointed away from the aircraft. As the aircraft accelerates, the compass needle points downwards, aligns with the dip. So basically my north tries to align, my north side tries to align with the vertical part, pulls the compass ball round, indicating a deviation, or basically moving the compass rose to artificially give a east. So now we know, gentlemen, that if I do a bank turn, when I'm flying north, my compass will actually read in the wrong direction. Okay, and it could go as far, depending on how fast that turn is, it could easily be 180 degrees out. That's why. So that's why we have the turn and slip, or the turn coordinator, combined with the stopwatch to work out our rate of turns. Okay, work out our rate of turns. So northerly turning error happens when the aircraft is flying north or the northerly direction. Okay, this is only true for the northern hemisphere. It's the opposite when we go in the southern, but we're only going to be asking questions on the northern hemisphere. Okay, and again, as Nepal's in the north as well, northern hemisphere, you don't have to worry more about it. The pilots go into big detail. They'll spend days in ground school going through this. Okay. Yes.
In this slide, there is the last line. The compass needles pivot downward to align with the magnetic dip.
Yep.
Can you explain this? Because the pivot is always up above the CG.
Okay. Right. If you look, I don't know if you can see. Right. If you look here, there's the north. Okay. That's what my compass. When I look at my direct reading compass, I look at it and I see north. But if you look here, this end, that's the north-facing needle. Agree with that?
Yeah.
That's the point to north. So now when I'm flying north, I'm happy because basically I'm flying along. My compass needle is lining up with the horizontal component of the Earth's magnetic field, and dip doesn't really have much effect. Now when I start, if you can see this, now when I start to turn to the west, so I'm going to turn to the west. Okay, the aircraft banks, but now dip grabs onto the north part of the needle and pulls it round. Okay, and if you can see here, the east is now pointing to the pilot, pointing to me. And it's all because of that dip. As soon as I start to bank, the needle dip becomes stronger than the horizontal component and basically pulls the compass rose round, giving it an indication to east. Okay, so without dip, my compass will work perfectly. With dip, the needle gets pulled round, or basically the needle gets pulled down to align with the vertical component of the Earth's magnetic field, giving me an incorrect heading. Okay, giving me an incorrect heading. And the faster and the steeper the bank, the more my error in my compass is going to be. Okay, so that's the first thing. Northerly turning error happens when the aircraft is flying north and turns east or west. So what causes northerly turning error? It's down to dip. Okay, down to dip.
And also in northern hemisphere, huh?
Only in the northern hemisphere. It happens exactly the opposite direction in the southern hemisphere, but we ain't going to talk about that. Okay. So now, if you look now, when I'm flying east, okay, when I'm flying east, when the aircraft banks, okay, to turn north, as you can see now, if you can see, there's east. Yeah, there's east. There's north. So now when I turn that way, the needle, if you look at the animation on the screen, as you can see, with my pen, as you can see now, when we're flying east and we turn north, the needle is already pointing to north. So when I bank, the dip is pulling it down, but it's already aligned with magnetic north. So it doesn't have any effect. So northerly turning error only happens when the aircraft is flying north and turning east-west. Okay? East-west. The other turning error, okay, is something called acceleration error, okay? Acceleration error. And again, that just basically causes the needle. Now, again, got my compass, but this time it happens when I fly north-south, east-west. So acceleration error happens when I am flying east-west. And what happens when I accelerate, okay, inertia, okay, when I accelerate, it pulls, okay. When I accelerate, it tips down, okay. And what happens is, there's my north needle, and it pulls it round to looking like it's going north. So if we do that again. So there's my north, there's the north side. I'm flying east-west, okay? I'm flying east-west. The aircraft accelerates. What happens is that dips down, okay? That dips down. There's my north needle. That gets pulled towards the vertical dip. And now you can see here, I have a north. So when I'm flying east-west and the aircraft accelerates, my direct reading compass will indicate a north, okay? It'll indicate like the aircraft is going north. It's still going east or west, it still goes north, okay? Now, if I decelerate, okay? Again, there's my north needle, okay? I now decelerate. What happens is the compass rose tips up, and again dips brings it down, okay? And you can now see on here it's indicating a south, okay? It indicates a south. So what we need to think about in acceleration error is what happens, okay? So acceleration north happens when we're going east-west, okay? Acceleration combined with the dip causes the needle to go north, okay? So acceleration causes it to go north. Deceleration causes it to go south, okay? And we use a little mnemonic to work that out. ANDS. Acceleration, the compass indicates north. Aircraft decelerates, the compass goes an indication of south. Again, all caused by dip, okay? Changing the centre of gravity of the compass rose. So remember that here, ANDS. When the aircraft accelerates, the compass shows an indication to north. And when the aircraft decelerates, the compass shows an indication to south. So remember that, ANDS. Okay.
This is in the case of aircraft is heading towards the north.
No, acceleration error happens when the aircraft is going east or west. Okay. Northerly turning error, okay, happens when the aircraft is going north or south. Okay.
During north and south, these acceleration errors does not affect.
North and south is northerly turning error. Okay. North and south, when the aircraft is going north and south, turns east-west, you get that northerly turning error. Yep. So, as in what it says there, northerly turning error happens when the aircraft is going north. And it will cause the aircraft to give and it goes east-west, it will show you an incorrect heading, either east or west. Yep. So northerly turning error only happens when the aircraft is going north and south. Doesn't happen when the aircraft is going east and west. Yep. Okay, and that's why we have that turn coordinator or turn and slip indicator. We look at acceleration error. That happens when the aircraft is going east and west. Okay, only happens when it's going east and west. If the aircraft accelerates, the needle or the compass will indicate that it's going north. And if the aircraft decelerates, the compass will go showing to a direction south. Okay, and it happens because the dip causes the centre of gravity to be not straightly down, and it causes a rotational force. Okay, so if you can just remember this word ANS, aircraft accelerates, compass goes north, aircraft decelerates, compass goes south. If you can remember that about acceleration error, and it only ever happens when you're going east or west. If you accelerate when you're going north and south, it won't make any difference. So you have to remember that when these two dynamic errors happen. Okay, you have to remember when the two dynamic errors happen. Northerly turning error is only when the aircraft is flying north or south. That's why we call it northerly. And the aircraft turns east-west, you'll get an incorrect heading. Acceleration error happens when the aircraft is flying east-west and accelerates. But in this case, you need to know what does happen. When you're flying east-west and the aircraft accelerates, the compass will show a turn towards the north. If the aircraft decelerates, the compass will show a turn towards the south. So acceleration error only happens east-west, no other time. Yep. Are we all happy in that basic understanding of northerly turning error and acceleration error, when they happen, and what happens, and why? The why is the dip affects the compass rose because the centre of gravity is not directly under the pivot. And that's the exact same for both dynamic errors. Normally turning error only when you're going north, causes the aircraft to go east or west. Acceleration error only happens when you're going east-west, okay? Only happens when you're going east-west. But what you do need to know is what happens when the aircraft accelerates. When you're going east-west, the compass will show an indication to the north. And when the aircraft decelerates, it will show an indication to the south. Okay, you have to understand those basic facts. Okay, anyone got any questions on that?
No.
Good. Okay, good. Right, let's get rid of all this. So just remember that there, and acceleration north, deceleration south. Unfortunately, I don't have a time to. Have I got time to show you that?
Hello, Ian.
Hello. Yes.
Can you also please send the links of these videos to Khagendra, to Mr. Yadav?
Yeah. Hold on. What am I doing? Hold on a sec. Oh.
Hello.
Hold on. I'll put them on the chat. I'll put it on the chat room. Probably the best bet.
Yeah, that would be good idea.
Thank you. Thank you, Ian.
Come on, copy. Hold on a sec. Can you all see that in the chat? Hello?
Yes.
Can anyone hear me?
Yeah.
Yes,
We have
yes,
See
sir.
that in the
link in the chat. Yeah.
Yeah. Hopefully that will explain it a little bit better, because it's very difficult trying to do 2 dimensions for a 3-dimension system. We'll have a little look at that later on. Okay. Or do you want to have a little look at it now? It's only 5 minutes long. All right, we'll come back. We'll come back to that. Right. So now we're going to talk about the sort of compass system you'll have in some of your aircraft. It's a gyromagnetic compass system. Okay, let's do a recap on gyros, and let's look at a recap on our compass. Going back to gyros. Remember, one of the properties of a gyro that it, for a short term, as long as it wasn't affected by external forces, the gyro, its axis kept pointing in the same direction in space. Yep. So in the short term, my gyro wouldn't precess. Yep. But in the long term, it will start to precess. So in the short term, over the next, say, 10, 15 minutes, my gyro will give me a very, very accurate compass heading. But in the long term, it will start to precess to give me an error. My compass, if I'm at 30,000 feet and I'm flying along and I'm not changing heading, my compass is very, very accurate. But as we now know, in the turns, in the short term, it's inaccurate. So what I need to do to fly is I need to get the best of both worlds. And what we're going to do is we're going to combine a magnetic compass with a gyro. Okay, and this gyro is a horizontal gyro. I'm going to call it a gyromagnetic compass. And the first thing about a gyromagnetic compass is it takes the best of a gyro, the best attributes of a gyro, the best things about a gyro, and the best things about a magnetic compass. Okay, and what we say is in a gyro, its heading is very good in the short term, but in the long term, it'll start to precess. A compass, its heading is very good in the long term, but is inaccurate in the short term during turns. So if I now take the best of both worlds, I am going to get an accurate system. That's called a gyromagnetic system, okay? A gyromagnetic system. So let's look at how it works. So now the compass, okay? Where did I put the damn thing? Okay, it's no longer a direct reading compass. Okay, we're not using one of these. We're going to use a remote indicating compass. This here is only an electrical device. Okay, coming out of this thing called a detector is a three-phase signal, and it's going to act like this little repeater, what we call a compass repeater, or the indicator in the cockpit. It's like a tiny little motor, and it turns, okay, to give the heading that the detector unit is giving. The heading, okay, this is my magnetic heading, okay, and we'll look at how it does it. So I've got a three-phase signal coming out there, and that is actually my compass heading. Okay, my compass heading, my CH, my compass heading. Now, as we know now, if I have a compass and it's anywhere near the generators, heavy motors, it's going to be affected by the aircraft's magnetic structure. So we need to make this detector unit, or my compass, my magnetic compass, I need to put it somewhere, as it says there, not affected by any stray magnetism in the aircraft. So what I'm going to do is put it in a part of the aircraft that's got the least interference by any ferrous or metal objects. And we usually put it at the wingtip or the top of the vertical stabilizer, the fin. Those boys in helicopters, we normally put it down the tail cone of the helicopter. Okay, now I put it down the tail cone of the helicopter. So in a remote indicating compass system, where would I put the detector unit? And that's this, my magnetic compass. I'm going to put it as far away from stray magnetic interference, i.e. the wingtip or the fin. And it says here the detector unit has lots of coils. Okay, we're going to look at this a bit more in depth and convert this as an electrical signal to feed the indicator. So it's good in the long term, just like any other compass, but it's bad during maneuvers. Okay, so when you're doing lots of turns, sharp turns, it's not very accurate. So we're trying to get rid of this inaccuracy because of the aircraft turning. So now we put a gyro in with the detector unit, okay? And what we're going to do is we're going to look at the signals, okay? We're going to look at the signals and we're going to see how we get an accurate compass indication, okay? We're going to look at how we get an accurate compass indication. So let's look at the basic, okay? Let's look at a very basic compass system, okay? A gyro compass system. So this is in the cockpit. Okay, it's the indicator in the cockpit. This detector unit, that's detecting my magnetic heading, okay? And we'll say that's in the in the tail of the aircraft. The gyro, okay, and that's a horizontal gyro. That could be, we'll call it, let's say it's an avionics compartment of the aircraft. And we have a fourth component, it's called an error detector. And that error detector will send out a voltage, okay? And that voltage is going to go to a torque motor attached to the gimbals, okay? And that's going to precess this gyro to give the correct heading, okay? It's going to give it like a direct heading. So what happens? Which one of these two indicators is the master? Okay, well, let's think about, gentlemen, a gyromagnetic compass, okay, is like a marriage. Okay, a gyromagnetic compass is like a marriage. Okay, I'm going to come back to, oh. Right, I've lost this slide. Where's the slide? Oh. Right, it's like a marriage. Now this here is what we call the error, okay? The error signal. And what happens, let's say the gyro, let's call that the man, okay, or the husband. How many people here are married? Any of you married? Yeah, quite a few of you. Okay, so you'll understand this, gentlemen. So you're the husband, okay, and actually the gyro actually gives the indicator in the cockpit. It tells it what it's going to do, okay? So it's just like you boys, okay? It's just like the man, okay? He goes down the pub, or he goes to the bar, and he tells all his friends, we're buying a new car, okay? We're buying a new car. We're buying a new car. So basically, you're telling all your friends, the husband is telling everyone he's buying a new car, okay? The detector unit is the wife, okay? The detector unit is the wife, okay? And it's just like you go back home, you've told everyone down the bar you're buying a new car, and she sits there and goes, we're getting a new kitchen, we're getting a new kitchen, we're getting a new, and she nags you until eventually you buy a new kitchen, okay? And that right, gentlemen? The wife is always right. Agreed?
Agreed.
Oh, no. Agreed, yeah. So you can see here, the gyro has the error, okay? So what happens is, this error detector, what the wife says is the direction. What will happen is, a signal will be sent out to the gyro. So if the wife says buy a kitchen or fly to 005, but this was 007, what happens is the gyro is precessed until it reads 005, and because that gives eventually gives the signal to the cockpit indicator to say 005. So in a gyromagnetic compass system, the wife is always right. Isn't that right, gentlemen? In a marriage, the wife is always right and the husband is always in error. Married people, is that correct?
Correct.
Yeah, good, thank you. So what I can actually say, okay, in a detector unit or a gyromagnetic compass, the detector unit of a gyromagnetic compass system is the master. Whatever heading it says, the gyro, even though it might be wrong, okay, it's eventually telling the indicator to read 005. It's what we call it's slaved. The gyro is slaved or synchronized to the detector unit. So whatever heading the detector unit says it is, because this is a compass, the gyro will be precessed to give an indication to the indicator of what the aircraft is heading. So the first thing to take out of this, what determines the ultimate heading in the compass indicator is the master or the detector unit. Okay, so what provides the master or what provides the ultimate indication of the compass? It is the detector unit. The detector unit, okay, is sometimes also known as a flux valve, okay? A flux valve, okay? We'll have a little look at that. So here's the flux valve, okay? The outside, it's usually a plastic container. And in that plastic container is a silicate fluid, which is there for dampening, okay? Which is there for damp. So therefore, can my detector unit be subject to liquid swirl? Yes, it can. Okay, we'll look at how we can reduce it, but it can still be affected by liquid swirl. There's the plug for my electrical connections, okay, because it's an electrical device. So let's have a look in here, okay. The first bit it says is number 1, okay. It's an electromagnetic compensator. Where did I put it? Remember I said in the direct reading compass we had the little bar magnets to reduce this deviation? Well, in the detector unit, they're not little bar magnets. It's in a little electromagnet. Two is an exciter coil. We're going to look at that later on. 3 is the flux valve itself. Again, we're going to look at that a lot more. At the bottom of this is a heavy weight. Okay. It's a heavy weight, so it's always getting pulled down straight, reference to the Earth's surface. Okay. So again, it's to reduce, it's putting the centre of gravity below the pivot point. So therefore, it's to compensate for dip. Okay, the angle of dip. And the next thing we have is what's called a universal joint. It allows the detector unit to rotate and tip round 360 degrees. Okay, round 360 degrees. So let's look at this flux valve again. There's the pendulous weight, keeping the pivot vertical reference to the surface. We have the dampening fluid, again, for dampening, but also can cause liquid swirl. Okay. This thing called a spider assembly is also known as the flux valve. Okay. For some reason, they call it a spider. Okay. Okay, you can see there's a heavy weight, it's holding it down, okay, relative to the Earth's surface. This here is what we call the flux valve. What happened there? Oh. Okay, or spider. I have never seen a three-legged spider in my life, okay? But that's what we call it. What we're going to look at is the construction of this flux valve, okay? Now, the first thing I want to look at is you can see it's divided into three sections, okay? It's divided into three sections. And each one of these sections has a leg, okay? Okay. It has three legs, okay? Three sections, equally spaced. So what I can say is each leg is 120 degrees apart, okay? This allows us, because it's 120 degrees, it allows us any signal magnetic field to produce a voltage in each of these legs that's unique for a specific heading, okay? Unique for a specific heading. So the first thing we're going to look at is this thing called collector horns. Think about it as a big funnel, okay, for the Earth's magnetic surface. So basically, any bit of the Earth's magnetic field coming in there, okay, gets all funneled into this leg, and we'll look at this leg in a minute. So the collector horns funnel all the Earth's magnetic field in that 120 degree arc into one of these legs, or this flux valve. And if you actually noticed, each of these what we call collector horns is laminated, okay? A magnetic field, a moving magnetic field, cutting a conductor produces a current, okay? And a current will produce, that current would circulate and it would produce an eddy current. And going back to mod 3, we know eddy currents are a loss. So we need to reduce these eddy currents. So that's why the collector horns are laminated. And if you can remember, laminations reduce eddy currents. Each spoke or leg, okay? We have three legs or three spokes. And they're connected to a primary coil, okay? And into this primary coil, I'm going to put an AC voltage, okay? So now I have an AC voltage in the center coil. And each one of those legs is electrically connected to this center coil. Okay, so what I'm actually going to get is, I'm going to get an AC also going down each one of those legs. And look here, wrapped round those legs is called a secondary pick-off coil. Okay, secondary pick-off coil. In reality, what happens is, this is where the Earth's magnetic field and the AC produced by this middle pick-off coil are detected. Okay. So what we can think about, ladies and gentlemen, this is very, very basic, like a very, very small transistor at the transformer. I've got my primary coil and my secondary coil. Okay. Depending on the ratio, what I produce in a transformer will be in the secondary. And without any Earth's magnetic field, that is what's going to happen here. But we're going to look at it a little bit more in depth, okay? We're going to look at it a little bit more in depth after lunch, okay? So I want to give a clear head before we start the next bit. Okay, so I make it 5 past. Okay, if we go for an hour, we're back at, back in an hour, gentlemen, after you've had your evening meal, or my case, lunch. Okay, so we'll go for a break for 1 hour, and then we'll come back and we'll find out how exactly my flux gate or my flux valve works. Okay, any questions so far? Okay, so back in 1 hour. All happy with that?
Yeah.
Okay, so we'll see you in 1 hour.
Yeah. Okay, sir.
Hello, gentlemen.
Hi.
Hello there. Oh, it's a big blizzard here today. Right. Oh. Just wait for the rest of them to come in. Okay, gentlemen, so just before we had a break, we're looking at this detector unit, okay? And we're looking at the various parts. The collector horns, which gathers all the Earth's magnetic field. We looked at the exciter, that's producing an AC, okay? And that AC will go down those spokes or those legs, okay? And then the secondary coil will pick off either plus that AC plus or minus the Earth's magnetic field, okay? And that's what it's going to pick off. So what happens here, okay? In my exciter, my primary coil, okay, what I'm actually going to do is I'm actually going to introduce an AC, okay? I'm going to put in here an AC waveform. And as we all know, gentlemen, our AC waveform is 400 hertz, okay? This is quite important, this 400 hertz, because we're going to use a bit of electrical magic, and we're going to make that frequency doubles. So what I can say at this exact moment, okay, when I've got a positive half cycle here, yeah, because this is connected to the negative side, I'm going to have a negative here. Yep, so basically, when we're doing the positive, I will get a positive half cycle here. And when I do the negative, okay, I'll then get a negative half cycle here. But because of this side here, I'll also get a positive on here. So now, for 1 hertz at the primary, I will induce, and that's my pick-off coil, two hertz, okay? So for every 1 cycle here, I'm going to produce 2, okay? That's as much as I'm going to go into how this works, because it's quite complex. But all you need to be aware, gentlemen, if the primary exciter coil produces 400 hertz, at the pick-off coil, we must have 800 hertz, okay? So basically the frequency of the AC at the pick-off coil is doubled. So just remember that fact, okay? Just remember that fact. So that's without any Earth's magnetic field. Now, again, what do we know about metals and Earth's magnetic field? Earth's magnetic field likes to go through metals. It doesn't like to go through Earth. And you can see here in this one, when there's no current going through the coil, all the Earth's magnetic fields want to go through the legs. And what happens is when I produce this AC, okay, it blows the Earth's magnetic fields out, okay? And what's going to happen, now you don't have to know this, all you need to know about what happens in the leg of the detector unit is the frequency doubles, okay? You've got a big diagram there how it works, but just you take into there. When 1 hertz goes in, 2 hertz are at the pick-off coil. Okay, so that's the big thing to remember on this. If I have 400 hertz at the primary coil, I will double it and I will get 800 hertz at the pick-off coil. Just remember that fact, okay? You won't be expected to figure out how it's done, but you can just basically see I've very basically gone through it. But just remember that fact, 400 in, 800 hertz. 800 hertz. Don't worry, Jen, it's not COVID, it's just a tea down the wrong way.
No worries, we are virtual.
That's right. Don't have any sympathy on me. I love yous too. Oh, right, where were we? Right, as you can see there, as it says there, 400 hertz in, 800 at the pick-off coil. If you just remember that about the legs, okay, that is most of the stuff that you need to go to on this course. The B2s will go into this a lot more. So now let's look at how this flux valve, okay, detects the Earth's magnetic field, okay. There we go, there's the three legs, okay. There's my collector horn. There's my collector horn. There's the leg. As it says there, one of these legs, okay, one of these legs will be straight down the longitudinal axis of the aircraft. So one of those legs will point in the direction that the aircraft's going to head. Now, if we look at this here, if I'm flying to magnetic north, the leg is flying directly to magnetic north. All the lines of the Earth's magnetic field hit this collector horn. And they all come down this collector horn. Okay, all come down this leg. But when it comes to the center point, if you look here, this voltage induced, these lines of magnetic field split. And if we can see here, okay, we can see here, hold on. At this point here, I must have maximum Earth's magnetic field. So all the way down to here, this point here, and then it splits. And I can say half go this way and half go that way. So now the voltage picked off here at the pick-off coils must be maximum this way. These two again are half going that way and half going that way, and that will give you a AC voltage which is going to move the compass indicator needle. Now let's look at this one. Okay, now let's look at this one. It looks like I've got 3/4 going through that leg and 1/4 going through that leg. But look here, I must have maximum through that leg. So the voltage induced here must be 3/4 of maximum. Okay, this one is 1/4 maximum. But look now, this is also maximum. But look at the direction compared to the first one. It was going maximum from the outside to the in. This will be maximum inside to out. So actually, yes, it's maximum, okay? But I could actually say that's negative, and that was maximum positive. So the voltages are different, and these voltages in each one of those legs for every single degree, so 360 degrees, the voltages in each one of those legs will be unique for each individual angle or each individual heading. So what we want to look at is does the maximum amount of magnetic field flow through one of the legs of a flux valve or one of the legs of the detector unit. So we can see here, okay, we can see here, look, I must have maximum, okay, when the leg is in line with magnetic north, okay? So maximum okay, so it says there, when I'm flying north, when I'm flying log, the leg it's in line with magnetic north will always have the maximum amount of magnetic field. Right, next thing, look at this one. If I'm flying east or west, that leg will have minimum magnetic field. So again, remember that. You could be asked or you're required to know in the detector unit, when is the maximum amount of Earth's magnetic field? In the detector unit, it's when it's flying directly towards north. When is the minimum amount in a leg of a detector unit? When is the minimum amount of Earth's magnetic field in a leg of a detector unit? When it's flying east or west or 90 degrees. Okay. So you've got to remember those two statements. Okay, you have to remember those two statements. So let's take this gyromagnetic system a bit more complex. Okay. So here's my detector unit. Okay, my flux detector, and we now know that is the master. That determines the actual heading that my compass indicator in the cockpit is going to read. But as we did say here, it gets its signal from the gyro. Okay. So now let's look at the system. We've got this slaving system. When we're talking very, very small voltages, the amplifier is going to amplify, and there's my possessional type. Basically call that my, that's my torque motor. Okay, we've talked about that already. We'll talk about vertical gyros. The next thing we need to talk about is this deviation compensator. Remember I said in the direct reading compass, to get rid of deviation, we turn little bar magnets to reduce it. Well, this deviation compensator is an electromagnet. And again, that's just going to do the exact same. It's going to reduce that deviation, okay? It's going to reduce the deviation. Again, my gyro, as a leveling system. Okay, again, this little electrolytic switches. And just to keep the gimbals, again, at the correct angle. Okay, so how does it work? So let's look at my compass, okay? There's my compass, and it's reading 0, 1, 0. My detector unit is reading 0, 1, 3, okay? 0, 1, 3. Let's look at this system, okay? It comes all the way through to here. If I have an error, this precession device force to precess the gyro, okay, to read 0, 1, 1, gyro, both the same, are reading
Hello.
Can
Hello.
anyone hear me? Hello, can you hear me?
No, little bit disconnected. It's
Who is
intermittent.
disconnected, Jan?
Can anyone hear me?
Yeah, now, not earlier.
Hello?
छोडेर गयो कसकोमा छ अब त्यो एक्सेप्ट गर्ने त्यो कसैकोमा छ आयो
That's better.
Yes.
Ah, thank you. I thought I'd look, well, it just completely dropped out.
It's technology problem, sir.
Yeah. The thing is, it's probably my end as well. Right, where were we? Yes. So, where was I before we got broken up? We're talking about the reducing the error. So, looking at this, the detector unit is going to tell the whole system what it needs to read, okay? In this error, the gyro is going to precess to give the indicator in the cockpit the correct reading. Okay, so it will precess the gyro until I get that heading there equal to that heading there. Okay, I'll just constantly precess the gyro until we get the two inputs reading the same. Okay, the two inputs reading the same. Okay, again, we've got a leveling system. Okay, no different to what we had in the vertical gyro. You've got your tilt switches, and as long as that produces, when it starts to produce, it'll apply a torque to precess the gyro back to the correct angle. Okay, so the two gimbals are 90 degrees to each other. Now, how does the pilot know? Okay, how does the pilot know that his detector unit and his compass are reading the same? Okay, because you think about it, if my compass indicator is 010 and my detector unit is 015, that's 5 degrees. And if I'm flying across the Atlantic and I've got a constant 5 degrees, instead of hitting New York, I'm probably going to try and land somewhere in northern Canada. So the pilot needs to know whether the detector unit and the gyro are reading the same. Okay, and this is where this thing called an annunciator comes in. Okay, what an annunciator, there's two types of annunciators out there. I'll draw the first one. It's a tiny little gauge. Okay, and this one particularly is what is basically called a noughts and crosses. Okay, and there's half the circle and there's half the cross. And when it's like that, you can see equals amount of the circle and equals amount of the cross. It tells the pilot that the gyro and the detector unit have got the same indication. Now, if there was an error, what would happen is this little shutter would move. Okay, so in this case, I would have all the circle and none of the cross, and it tells the pilot, okay, just like here, it tells the pilot that the system are not synchronized or slaved. Okay, not synchronized or slaved. Now, there's another type of annunciator. It works in the same principle, but just looks slightly different. Okay, it's a gauge. It's got a little pointer. It's got a couple of marks there, a couple of marks there. And all that happens is the pointer will go left or right, and it tells the pilot, okay, it'll tell the pilot whether his reading of the compass is greater or less than it's actually indicating. Okay, we will have a little look at how that works right now. So that's the two types of annunciator. So let's look, see what happens. And as long as, okay, as long as the indicator and the detector unit are reading the same, okay, at this control transformer, or let's go back to what we called it before, error detector, as long as that reads 0, 1, 0, that reads 0, 1, 0, there is no error, okay? There's no error, therefore nothing goes to this amplifier, nothing goes to the gyro, to torque motor to precess it, and this little annunciator stays in the middle. Great. Now let's look what happens when we get an error, okay? So now my compass indicator and my gyro are both now reading 0, 1, 0, okay? And my detector unit is reading 0, 1, 5, okay? Coming out of the error detector, I've got an error, and this voltage will be equal to 0, 0, 5 degrees, okay? This error will be amplified. It does two things. It sends a voltage to this annunciator, and basically what that's going to do is going to move that little shutter, and moves the shutter across one of the crosses or the circle, and that tells the pilot that the output from the detector unit and the output of the gyro are not the same. At the same time, coming out of here, we also send this voltage to the torque motor, and it now starts to precess the gyro. And the gyro will turn, okay, 0, 1, 1, 0, 1, 2, 0, 1, 3, 0, 1, 4, and 0, 1, 5. And again, that's going to go to 0, 1, 5. And at that point, okay, I no longer get any error. No voltage goes to the torque motor. So it stops precessing the gyro. And my annunciator's gone back to its synchronized position because the detector unit and the gyro are reading the same, okay? So what we have to take out of that, gentlemen, is what is the purpose of the annunciator? The annunciator is to tell the pilot when the output from the gyro is equal to the output of the detector unit, okay? And that is the big purpose of the annunciator. So remember what the purpose of an annunciator is. Now, we've got this, what's called an MHAR system. It just allows us to have everything remote from the cockpit, but it also allows us to send information to other systems in the aircraft, okay? Other systems in the aircraft that need, okay? It need direction, okay? It need a direction. Things like autopilot, flight director, information to your flight data recorder, all these information need heading. Okay, so our magnetic heading reference system is very, very similar in principle to how a gyromagnetic compass system will work in any aircraft. So the compass system is just not providing information to the pilot, it's also sending information to other systems in the aircraft, okay? Other systems in the aircraft. Okay, I know we're going to look at here, we're not going to go around this too much, but you can see coming out of here, coming out of the computer, we have heading signals to flight director. You can have flight director, autopilot, etc. So in a magnetic heading system, the electrical input, okay, the electrical input can go to other systems in the aircraft, okay? Just like flight director and horizontal situation indicator. Now, depending on the type of aircraft, very few of you will see an indicator like the one on the left. This one in the middle is called an HSI, a horizontal situation indicator. It provided not just the pilot with his heading, his directional information, but provided a whole load of information for your radio navigation aids like ADF, DME, ILS, glide slope, etc. Those who are working on the A320, this is what you'll see. Remember, you've got your 6 TV screens in the cockpit. This is your navigational display. So now it's not sending a voltage to move an indicator, it's sending a voltage to a computer, and that computer is going to interpret that voltage and make it a TV picture. Okay, and that will be displayed on my navigational display. Okay. Are we all happy on the compass systems, gentlemen? Okay, we're all happy on compass systems. Does anyone want to go through anything again? Anyone?
Sir,
No?
explain once again enunciator.
Say again, please.
Enunciator, sir.
Annunciator.
Yeah.
Right, hold on. I think I've got a better picture. Give me 2 seconds. I think I've got it. Oh, Who was that? Who was that asked the question?
Sanjay, sir. This is Sanjay.
Sanjay, right? Okay, Sanjay. Okay. Now, agree, Sanjay. Which finally, what finally, or what determines what the compass indicator in the cockpit is reading? Is it the detector unit or the gyro?
Gyro, sir.
Yeah, but what ultimately depends. The gyro, yes, you're right, is connected to the indicator, but which one has the correct, or which one has the master, which one has the ultimate say in the
unit?
Pardon?
Master is the detector unit.
The detector unit, yeah. So basically, whatever the detector unit says should indicate on the indicator. But as we've already said, that the indicator is directly connected to the gyro, so that this gives the information. And this the annunciator, okay? And the annunciator tells the pilot whether the detector unit and the gyro are what we call synchronized. Okay, therefore they're reading the same. So the annunciator tells the pilot if they're reading the same. Okay. If they're not, okay, and in this particular case, there's a little shutter, moves across the X in this case, and tells the pilot they're not aligned, okay? And what happens here is the output of the detector unit, okay, and this control, what we call a CT, is a control transformer, but we call that, let's call it the error detector. Now, if this is reading, put an output for 015, and the gyro is saying 010, would you agree there's an error of 5 degrees, Sanjay?
Yes, sir.
Right. So that 5 degrees error, the error detector gives it as a voltage. And that voltage will go to this amplifier, which makes that annunciator tell the pilot he's got an error. But at the same time, that voltage goes back to the torque, okay, the torque motor at the gyro, and now starts to precess the gyro. And it's going to precess the gyro to match 015. So it'll start a voltage, it'll precess to 010, 010, 011, 010, 012, 013, 014, 015. And once it gets to 015, is there an error, Sanjay, between what the gyro is indicating and the detector is indicating?
Yeah.
Sanjay, no, is there an error?
No, there is no error now.
There's no error. If there's no error, there's no longer any voltage going to this amplifier. Therefore, there's no voltage going to the torque motor. If there's no voltage in the torque motor, it stops precessing. That annunciator goes back to the position to tell the pilot that the detector unit and the gyro are synchronized, therefore they're giving both the same heading. Okay, both
Okay, thank you, sir.
the same heading. Yep.
Yeah, I got it now.
Right, couple of little things. For some reason, I have lost a slide. Hold on, let me just check. I seem to have lost a slide. Hold on, give me 2 seconds. Okay, don't know where it's gone. An up-to-date slide. Right. Right, this thing, look at this now. This synchronizing, this precessional force, okay? Okay, and what we call so basic my normal come on, give me a break. It doesn't want to stay in that page, right? So this synchronization has 2 levels, okay? We have oh, come on. Okay, Normal synchronization. That will precess the gyro at 3 degrees per minute. So you come out of a turn, you might be 1 degree out, and if it normally goes at 3 degrees per minute, 20 seconds later, it's working fine.
Sorry, but I'm a little short. This is real rice. It's got to be worth something.
Okay, aircraft comes to your hangar.
Arschloch. Der Übersetzer funktioniert
Aircraft
wieder
comes
mal
to
nicht.
your hangar, and it shuts down, switches
Geht
off
auch
the
immer das
power.
Geld.
You take it into the hangar, you do some work on it, and the next day you bring it out, okay? And when the aircraft shut down, it was reading south, 180 degrees. But the wind has changed, okay? And you turn the aircraft round, so my aircraft is now parked, heading north, okay? I now power up the aircraft. How long would it take the gyro, okay, to be precessed to align or synchronize with the detector unit if it's going at 3 degrees per minute? Anyone?
1 hour.
No, it's 3 degrees per minute and you're 180 degrees out. So 180 divided by 3 gives me
60 minutes, around 1 hour.
60 minutes. Yeah, 60 minutes. Yeah,
1 hour.
that is a long pilot's pre-use or startup checks, isn't it? So we can't wait an hour. Okay. So what the aircraft has also got something called fast synchronization, and we actually see in our notes it's 600 degrees per minute. So pilot's got a little switch in his cockpit, and he can what we call fast slave. So basically, it takes roughly again 20 seconds. So it was 180 degrees, about 180 into 600 is just over 20 seconds, about 23 seconds, rather than waiting 60 minutes. So the fast synchronization rate is 600 degrees per minute. Please remember that. The normal synchronization rate is 3 degrees per minute. Okay, so the normal synchronization rate is the automatic synchronization of my detector unit to the compass. The fast slaving rate, the pilot has to do it himself, and again that is 600 degrees per minute. Right. One last thing on this before we go, gentlemen, on to the next section. Okay. Now I've got to say, 26 years working on aircraft, okay? I know of, well, I replaced one detector unit in 26 years. And also in that time, I know of one other detector unit. And we had 32 helicopters, okay, 32 helicopters. And in 26 years, I changed one. I know of one other that was changed. So they're very, very reliable. But there's going to be situations where the detector unit becomes unserviceable. Okay, for whatever reason, it becomes unserviceable. And if that has no output, okay, no voltage, I'm always going to have an error. The compass is going to try and keep precession itself. So what the pilot has the facility to do in the cockpit is what's called a DG switch, directional gyro. he can actually take out the detector unit. And it's just leaving the gyro to give my compass indication. And we now know in a gyromagnetic compass, a gyro is good in the short term. Okay. And all the pilot has to do is he'll look at his standby compass and basically precess the gyro to get the correct heading. Okay. So if the detector unit was to fail, okay, is able to switch out the detector unit and it's working as a normal free gyro. So please remember what the purpose of an annunciator. It tells if the detector unit and the gyro are slaved together. We've got a normal synchronization rate of 3 degrees per minute. And we have a fast slaving rate of 600 degrees per minute. And if it fails, we can actually go into what's called directional gyro, where we take out the detector unit and the compass system is only relying on the horizontal gyro to give us our steering information. Okay. Are we all happy on that, gentlemen?
Okay.
Happy.
Good.
Sir,
Yes.
this when the detector unit fails, it acts as a normal gyro, you said?
Yes.
And
so
the compass gets the information from
Say
horizontal
again,
gyro.
please. Say
So
again.
at that time, compass get the information from horizontal gyro.
Yeah, it's only getting. You look there. I take that information out. So basically, whatever the gyro is indicating will be on the indicator. Okay. Because remember, I said on a short period of time, and I think it says it's up to about 20 minutes. It's accurate, but then it will start to wander. Okay, it will start to drift away. And what the pilot will do in reality is he'll drop down his standby compass, and all he'll do is he'll precess the gyro to get the reading correct. Okay, so he does that manually. So there's no automatic system now.
Okay.
Okay.
Thank
you. Lovely. Right. So the next thing we're going to look at is stall warning. Okay. Stall warning. Now this is going to cover all aircraft. This is going to cover aircraft from the smallest private aircraft to your most computerized A380, A350, 777. Just be aware, gentlemen, the only aircraft that don't have a stall warning system are helicopters. Okay, but unfortunately, gentlemen, those who are still helicopters, you still need to know this. Okay. Okay, this is what one of the things the pilots get told. If you want to go up, pull back the stick. If you want to go down, pull back a little more. If you want to go down real fast and spinning round and round, just keep pulling back, okay? Because basically you'll get to the point where the aircraft stalls. Right, we're going to look at the first basic stall warning system, okay? This is what we call a Hold on, where's it gone? Where's the... Yeah. Here is the first one you're going to look at, okay? It's the angular tag vane, okay? It's a vane. And if you actually look at it, it is like a little aerofoil. Okay, it's a little aerofoil. And what that wants to do, what it wants to do is stay in line with the airflow of the aircraft. Okay, wants to stay in line with the airflow of the aircraft. We'll look at two different types. Okay, we're going to look at the vane and we're going to look at something called the probe. Okay, we'll look at the vane and we'll look at the probe. So in a cockpit, and again, you're going to have it on your EFIS screen. There's your angle of attack, okay? Old aircraft, you'd actually have, there's the wing. In the green zone, you've got enough lift. The yellow zone, it's not looking good. In the red zone, you're going to die. So how does it work? So here is my angle of attack probe, okay? And it will always stay in line with the airflow of the air. So when the aircraft starts to climb, so here's my airflow, my relative airflow. There's my little vane, okay? Little vane. And when the aircraft is level, it's flying straight into the air. The airflow, again, will keep the vane straight in line with the airflow. Now, as the aircraft, you can see here, starts to climb, it's still going forward. And there's my relative airflow. And there's my relative airflow. So what happens here is there's my little vane, okay? It's staying relative to the airflow. And what you've got is a little three-phase synchro. And the vane is attached to the rotor of that synchro. So when it moves, it's going to induce different voltages into each one of those coils. And that's basically going to cause this little pitcher, okay, to move up and down, or the pointer to give me the angle of attack. Okay, the pointer to give me the angle of attack. So that's the vane. Okay, then we have the probe. Okay, then we have the probe. It works on pressure. That's the probe here. Okay, and if you look there, it's got little slots. Okay, and it's got two banks of slots, one at the top and one at the bottom of the probe. And how this works, okay? What I'm going to do is I'm going to put a little pressure transducer at the end of each of these, okay? And that's going to be connected to a little amplifier. So now the aircraft is flying straight and level. And you can see here the upper and lower slots, they're tilted up, okay? They're tilted like that, out. But can I see now that in straight and level flight, the pressure here, okay, let's call it 10 psi. Because it's straight level, must be the same in the bottom, which is 10 psi. Let's say that gives out, comes to little pressure, that produces 10 volts. This pressure transducer, oh, come on. Produces 10 volts. Oh, for goodness sake. Now when you come to the, here I've got 10 volts going in, 10 volts coming in. Therefore, I've got plus 10, negative 10. I have 0 volts coming out. And that would go to my angle of attack indicator. I've got 0 volts, therefore it doesn't give an indication. Doesn't give an indication, or doesn't move. Now let's look now, the aircraft starts to climb, okay? The aircraft starts to climb. Again, I've got my two little pressure transducers. Again, they go to a little lamp. Oh. They go to a little amplifier. They go to a little amplifier. Let's call that plus or minus, and that goes to my angle of attack indicator. Now, if you look at here, the bottom one is directly in line with the airflow. So let's say that we call that, okay, we call that 15. This one here, because it's now out with it, let's say it's now 5. So we've got 5, 15, okay? We've got 15, we have 5, therefore we've got an output of 10. That 10 volts will cause the angle of attack indicator to give the wing, okay, to show a climb. And that's how that system works, okay? That's how the fixed probe works, okay? The fixed probe works. Now, one of the ones, so that's the fixed. There is now what's called a rotating probe, okay? And what it does, okay, is similar. The probe looks very, very similar to the fixed probe. But what the system is going to do is going to make sure that the probe, the vents of the probe are always pointing in the direction of the airflow. Okay. So what we're going to have to, that's going to come out to here, and that's going to go to the angle of attack indicator. Okay. Now, if you look here, both pressures are the same. Electrically, what we're going to do is send this motor, and if both the pressures are the same, nothing happens. Okay, we're in straight and level flight. Now let's look what happens when the aircraft starts to climb. Okay, the aircraft starts to climb. What happens here, you can now see the airflow is direct to here. And there's only a small amount getting here. So now we're going to get a voltage, and it's going to go to this motor. And as I've said before, it's now going to start to drive the angle of attack indicator. But at the same time, this output drives the motor, which drives the rotating angle of attack vane into direct airflow. So again, the pressure at P1 and P2 are the same. And at that point, the angle of attack indicator stops moving. Oops. Stops moving. And that's how they know the aircraft angle of attack. A rotating angle of attack indicator, having talked to the mechanical guys, is more for supersonic aircraft. So things like Concorde would have had it. That type of angle of attack indicator. Okay, are we happy on how an angle of attack indicator works? Very simple. Okay, next thing we're going to look at, gentlemen, is the stall warning systems you have on your aircraft. Again, we're going to look at from the most basic aircraft to the most complex aircraft in the system, okay, in the aircraft. So we're looking at a very, very basic one to the most computerized system, okay, to the most computerized system. So the first thing we're going to look at is what's called the pneumatic stall warning system. The pneumatic stall warning system. Just give a bit of a description. This little trumpet, okay, this little trumpet is in the cockpit of a little, see here, this little Cessna. There is an open vent on the front leading edge of one of the wings. Now, let's just get this system in our heads. So inside the trumpet, which is going to make the noise, is inside the cockpit. It's connected to this little vent on the leading edge of the wing. Inside, let's think about air. We've got to think about air. When I start to get towards the angle of stall or the critical stall angle, the air here becomes turbulent. Okay, in turbulent air, the pressure goes down. Okay, pressure drops in turbulent air. This, remember, this is an unpressurized aircraft. This is in the cockpit. The trumpet is in the cockpit, and it's in still air. Okay, inside the cockpit is still air. So how does it work? As the angle of attack of the wing starts to increase, the more and more turbulent the air at the leading edge of the wing becomes. And the pressure at the leading edge of the wing starts to drop. And what you have here is you have a lower pressure here and a higher pressure in the cockpit. And what happens is the air is sucked the air is sucked out of the cockpit through this little trumpet. So it's sucked out of the trumpet, and it's dragged out by the vent at the leading edge of the air. So basically that high pressure air is pushed through there, through the pipeline to the leading edge of the wing. And as it's pushed through the trumpet, it makes a honk, big honk sound. That's all it does. And that tells the pilot he's actually got to the critical stall angle. And if he doesn't do anything else, he's going to stall and he's going to die. Okay, so how does a pneumatic stall warning system work? Is when the pilot's wing approaches the stall angle, the air at the leading edge becomes turbulent. Okay, turbulent air, the pressure reduces. And as we all know, air, high pressure air always wants to go from high pressure to low pressure. It's still air in the cockpit, it's pushed through this little trumpet, it makes a sound, and that tells the pilot he's actually at the critical stall angle. Are we all happy on the pneumatic stall system in a aircraft? Pretty simple. All happy in that?
Yes.
Good. The next one we're going to look at is what's called a stall warning vane. A stall warning vane. This is an electrical system now, okay? And it's an electrical system. Again, usually found on, this is probably more high performance private or piston engines aircraft. And what we've got here is a little vane sticking out from the leading edge of the wing. And if you look at the right hand side here, here's that little vane. It's connected to a micro switch. And now, as the aircraft starts to, the leading edge starts to get to the stall angle, this turbulent air, okay, I'll get to the point where it lifts this stall warning vane. It completes an electrical circuit, okay? It completes an electrical circuit and it will activate several systems to tell the pilot that he is approaching a stall. The first one will be, okay, I'll get into it. Okay, the first one will be, give me strength. It'll be an audible warning, okay? Usually a bell, okay, to ring. It'll get a visual warning. With some flashing lights. And then on top of that, you'll get a stick shaker. So on my stall warning vane, okay, it's a little vane that when the aircraft approaches the stall angle, the turbulence causes the vane to lift up and completes an electrical circuit. It activates 3 systems in the aircraft. An audible, which is usually some sort of bell. It puts on some flashing lights, tell him he's increased it, and he gets something called a stick shaker. Okay, so please, understand the operation of the stall warning vane, and understand what the three systems it produces, okay, or three systems it activates. Audible warning, visual warning, and a stick shaker, okay? Now, a stick shaker. Are we all happy? Now, there's a few helicopter boys in here, and you've probably never felt a stick shaker, okay? And again, until I started teaching this subject, and I went down to British Airways onto the A320, and they got the stall warning system to work, I couldn't believe how violent that stick shaking is, okay? Any of the gents who are on the 320s, has anyone else felt the stick shaker work when you've functionally tested the stall warning system? Anyone?
Yes.
How violent is the stick shaker?
Yes.
Is it the shake back? Is it very big shaking?
Yes.
Yeah, it does. It really shakes the pilot. Okay, and a stick shaker is a DC motor. Okay, a stick shaker is a DC motor, but attached to the motor is an off-centered weight. Okay, and it basically puts out, it's out of balance weight, and that's what it shakes. So understand what a stick shaker is. It's a DC motor, okay, that will, okay, it's a DC motor that will violently shake the aircraft. Okay, and we're now looking at a modern computer system. Okay, oops. We're now looking at a modern computer system. Stall warning computer. Yes.
Do we helicopter guys have to study this stall warnings and
Unfortunately, yes. Okay.
For exam?
Yes, they have to, because instruments are common. It's a common subject. Okay.
Yeah. Okay.
Okay. Unfortunately, that's it. You'll never see a stall warning, because it doesn't mean the helicopters can't stall. It's just they stall in a different way to fixed wing aircraft. But please remember, okay, what you could be asked. So for stall, okay, a stall warning computer has all the programmed information about the aircraft. And if you've done aerodynamics, you'll understand that stall, the angle of stall, will change depending on the speed of the aircraft, if he's got any flaps out and the angle of the flaps, and if he's got any slats out and the angle, combined with that, the speed of the aircraft. Okay. So let's look at this information. So inputs into a stall warning computer are slap position, flap position, the angle of attack. The air data computer gives them the airspeed, okay? The airspeed. So please be aware of the inputs into a modern computerized stall warning computer. The last one down there, it says an air ground switch. If the pilot's landed, okay, and he's taxiing or he's going down the runway, he can't stall. So basically, the air ground switch tells the stall warning computer he's on the ground. And that could be as simple as some sort of weight on wheel switch. Let's look at the outputs from a stall warning computer. The first thing, warning lights, okay? Usually, for those who in the computer, an A320, it will be in the primary flying display, and it'll come up in a big red background and it'll say stall. The next thing you're going to get is the audio warning. And in this type of aircraft, it's a voice. It'll go stall, 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 stall. It still has a stick shaker. The pilot's control column will vibrate. The next thing, okay, this is computerized. This is the computers taking over the world. We all know now, if you've done aerodynamics, if the aircraft goes into a stall, the best way to recover it is to push the nose down. Push the sticks forward, get the nose down, get some forward speed. In a stall warning computerized aircraft, that's exactly what the computer does. It pushes the control column forward to get the nose down, to get speed, to provide some lift. At the same time, it can actually deploy the slats, increase that chord length, increase the lift for a certain speed. So you are required, gentlemen, to understand the inputs into an aircraft stall warning computer. And you are required to understand the outputs from a stall warning computer. Okay. As we said there's your stick shaker, and again it's a basic DC motor with a unbalanced weight in the end. Now let's look at a computerized system. Okay, there's a couple of regulations. In fact, we'll go for a 10-minute break, gentlemen. Okay, we'll have a 10-minute break and we'll finish off the computerized stall warning system. Okay, 10-minute break.
Okay.
Yeah. Hello, gentlemen. Are we all there?
Yes.
Okay. We'll now look at the computerized stall warning computer. Now, we're just going to look at a basic system, okay? And what we're going to say is a basic system. There's going to be 2 stall warning computers. I'm going to tell you now, in reality, you're going to have at least 3 stall warning computers, okay, in your aircraft. But it doesn't matter which one. If we've got 2 or 3, the regulations for these systems are the same, okay? All that we are doing, if we put 3 in, we're going to have an extra layer of redundancy, okay? So ideally, we want 3. But even some of the most basic Learjets, some of the little turboprops, will have at least 2 stall warning systems, okay? And the first thing is, each pilot will have its own stall warning computer, okay? Each pilot will have its own stall warning computer. So you can see here, the captain's comes off, it's powered from the essential bus bar, okay? And we'll find out when we do power supply that the essential bus bar is always powered. Okay, so no matter what happens to the aircraft power supply, this stall warning computer will be powered. The non-essential, okay, if something fails, that might not be powered. So first thing, in the event of a power failure, we can have at least 1 stall warning computer working. And that's one of the regulations, is the stall warning computers between the pilots and the co-pilot, they must have individual power supplies, okay? They can't be supplied from the same power supply. So, first thing is, stall warning computers between the pilots and the co-pilots must have different power supplies, okay? Now we've actually looked at the inputs. The inputs between the pilots and co-pilots are no difference. And what we talked about, angle of attack, airspeed, air ground switch, slats and flaps information, that's the same as what we've done there. And the outputs are the same: automatic slats, stick shaker, the warning on your primary flight display, your audible warning, and the stick pusher. They're the same, okay? But let's look at what might happen if one of the systems fails. Let's say, and it doesn't matter which computer system fails. Let's say this computer fails. For whatever reason, it fails. If the co-pilot or the first officer was the flying pilot, he still needs to know if there's a stall. So what happens is, here is as soon as one computer fails, there's a little bypass connection. So now when the pilot's stall warning computer triggers, it will trigger the co-pilot's. Okay, so in the event of one stall warning computer failing, the other one will still cause the other computer's systems, right here, the first officer systems, to trigger. Now let's look at the system. We're working as normal. Okay, we're working as normal. Now remember, independent power supplies. And what I could probably say is, all this information here, okay, going into my computer is also independent. So let's say I have the airspeed switch, okay, the airspeed coming from the pitot tube, or this side here, okay, is from the left-hand side of the aircraft. And this one is coming from the pitot tube in the right-hand side. Here's my little aircraft looking, okay. Now, there's the two pitot tubes. One like that, and one like that. If I'm coming straight into wind, that's not a problem. Both will be reading the same. But now, if they're that direction, yeah, that direction, we can see this one's going to have a higher airspeed than this. So what you might find is that's got slightly higher, but again, the lift on this side, on the port side, is slightly down. So now I can say that the left stall warning computer, its airspeed is going to be less. So its airspeed is going to be less. And if we've done aerodynamics, you know if the airspeed's less, my stall speed is also going to be less. My stall angle is going to be less. So now I can actually quite happily say that my left hand on my captain's stall warning computer, it will activate before my co-pilot's. But I just don't want the captain's systems to vibrate, because if the first officer is the flying pilot, he doesn't get the warnings. So going back to this bypass again, as soon as one stall warning computer activates, it will trigger both pilots' stall warning devices, stick shaker, lights, audible warning, slats and flaps, okay? So remember that. So what are the regulations regarding computerized stall warning supply? They must have, each computer must have a different or an independent supply system. If one stall warning computer indicates a stall before the other computer, the first computer to trigger will also trigger the other computer's warning systems. Okay, so remember that. So you need to be aware of, when you look at a computerized stall warning system, you have to recognize the inputs and you have to recognize the outputs. We have to look at the regulations. Each stall warning computer must have an independent power supply. And if one stall warning computer activates before the other, the stall warning computer that activates first will activate the other's stall warning systems. Okay, are we all happy on the computerized stall warning system of the aircraft? Are we all happy on that?
Yes.
Good. That's a bit more complex, but yeah. Right, now we're going to look at the basic glass cockpit. Okay, now as we've said already, we've talked a lot about the analog gauges. just be aware that majority of the sensors are the same, whether it's analog gauges or an electronic flight instrument system, a glass cockpit. Rather than the gears moving pointers, the gears will move electrical pickoffs and provide a voltage which will go to a computer. So what we've talked about in analog gauges, etc., still is valid for an electronic flight instrument system. Okay, so this is what you're used to. Okay, of some sort. I know this is an Airbus. Okay, it's an Airbus, I think, isn't it? Yeah, it's an Airbus. Couldn't see from there. And the electronic flight instrument system consists of 6 displays. Okay. 6 displays. Those who are working on the A320s, is your displays, are they LED or are they cathode ray tubes? Can anyone tell me?
They're LED.
LED. Okay. I completely agree with you. 2 years ago, I went to one of the British Airways depots, and I was just getting a bit of a show around the A320s that they have. And their electronic flight instrument displays are cathode ray tubes. Yeah, I was surprised at that as well. So it's just like when you go and get a car, you can buy all these optional extras. But it doesn't matter how, if it's LED or LCD, it doesn't matter. How the information gets there is the same. Okay. There's 6 displays, and we'll look at these 6 displays as we go through. Okay, and they're numbered 1 to 6. Starting from the left-hand side, okay? The pilot's primary flying display is called display unit number 1. The pilot's navigational display, the second one, is display unit number 2. The ECAM system or the EFIS system, depending if you're Boeing or Airbus, the main engine information or the upper display is display unit number 3. The bottom, okay, the bottom display, the bottom ECAM or EFIS system, which has got the secondary engine and systems information, is display unit number 4. If we keep going, the co-pilot's navigational display is display unit number 5. And again, it goes to the co-pilot's primary flying display is display unit number 6. And if you can see here, it goes back to one of the very first things we did on day 1 is we looked at the regulations talking about instruments from ICAO. I remember once they said that they have to be symmetrical down the line of the aircraft. Well, you can see here, 1 and 6 are on the outside. 2 and 5 are next, and these 2 are straight down the middle. Okay, so even though we've got the glass cockpit, we have actually still meeting requirements of ICAO. So 1 and 2 pilot side, 5 and 6 co-pilot side. 1 and 6 are primary flying displays, 2 and 5 are navigation displays, and 3 and 4 are your EFIS or your ECAM system. 1 and 6 primary flying. Yes.
In this system, in helicopter, the pilot and the co-pilot seats are differ, and how it differ.
Yeah.
How would we know that?
Yeah. Okay. Yes, the pilots and the co-pilots on rotary wing sit in the opposite seats. Okay. From my basically, it would still be numbered by the pilot. Okay, so the pilots will be 1 and 2. The electronic flight instruments displays can be slightly different. In helicopters. Okay, can be slightly different. Okay, but if we just remember these numbers for in here. Okay, for the exam. Okay. It saves trying to complicate things between helicopters and fixed-wing aircraft. Two and 5 navigational displays, and 3 and 6 is your ECAM or your engine warning displays. Okay. So, electronic flight displays. The primary flying display is your primary flight information. Primary flight information. Now, if we look at the primary flying display, I'm going to tell you there's at least 6 or 7 instruments on there. Okay, 6 or 7 instruments, but the main one is, okay, so the primary flying display, as it's known, will show primary flight data. Okay. Right. Well, what I want to take into this, if you look at the main information, okay, it is my okay. So my primary flying display, its main function is to take over or provide what the information of the attitude indicator was. Okay, the pitch and roll information. So what information did what gauge or indicator did the primary flying display take over? It took over the main information of the attitude indicator. Okay, display units 2 and 5. Okay, all your navigational information. Okay, and as it says there, it's taken over from the horizontal situation indicator. Okay, it's taken over from the horizontal situation indicator. But on top of this, your navigational display can put all your radio navigation aids in. It can put TCAS in. Okay, we'll look at that later on, TCAS. We also can put on weather radar. Okay, but primarily it's taken over from the HSI, the horizontal situation indicator. And your display units 3 and 4 are all your main ones. 3 is your main engine systems. 4 is your not so important engine systems and what we call status displays. Okay, what are the condition of certain things? And I think that we give you there. Are the doors locked? Is the ventilation on? What's the power of the hydraulic? What's the pressure of the hydraulics, the pneumatics? What's the power supply of each of the generators? So that's what's in display units 3 and 4. So here's a highlight of a view graph of the display units. Okay, 1, 2, 3, 4, 5, 6. So we can call that okay. So you can now see here, DU1, 2, and 3 are fed off something called a display electronics unit. And 4, 5, 6 are fed off another display electronics unit. And we call these DEUs, okay? Display electronic units. Yes.
The navigation display, can you go one again, the slide? I want to see the informations.
So if you can see here, if you look round the top, there's your compass. Yeah, that's the main compass information. But on top of that, we can also have other navigation information, like it says there, radar, VOR, DME, TCAS, ILS, and I can also put weather radar onto that screen as well. So now, when we had the horizontal situation indicator and HSI, we had a compass and maybe a couple of navigation aids. Now on the TV screen, it can tell you, if you look here, there's my aircraft. It can tell you there's other aircraft around. It can tell you the heading. It can tell you there's my airspeed. It's got VLR selected. It's probably got a few other things. It's got the range. I can put a whole load of other information on there. It's the one thing I would say that has actually increased the pilot's situational awareness. Okay, you all happy on navigational display?
Yeah.
Good. So we're going to look at how the pilot's displays get their information. Okay, how the pilot's displays get their information. Yes.
In this engine, the 3 and 4, what do the fourth one says?
Okay, so the third one, okay, the 3. So this one here's number 3. For goodness sake, give me strength. That's number 3. That's number 4. Okay, let's call that main engine. Okay, information. Like your N1, your EGT, N2, etc. Okay, all the information the pilot really needs to know about his engine all the time. DU4, okay, we might have all the not so important engine information like temperature of the oil, okay, vibration monitoring will all be in there. But also we have, so basically that's got engine information, yeah. We'll call that secondary engine. And then we also have what's called status display. And it tells you the status of what the systems in the aircraft are actually doing. So as you can look on the picture here, it tells you are all the doors are locked and armed. It can also, on here you've got lots and lots of pages, okay? You might have up to, I think it's A 737's got up to 13, I think it's 13 pages on here. It'll have a page for hydraulics, and it'll tell you what the temperature and the pressure of each of the hydraulic systems. Most of your aircraft's got at least 3 hydraulic systems, so it'll tell you the temperature and pressure in each one of them. It'll have a page for pneumatic systems, so it'll tell you the pressure in the pneumatic systems and the temperature. It'll look at the electrics, so it'll tell you the output, the voltage, and the current coming out of each of your generators. The voltage coming out your battery, your TRUs, all the electrical systems. It will have the status of all the systems. And also on this page here, we don't mention it in notes, because also the status if, let's say, number 1 generator failed. Okay, it tells you number 1 generator's failed. There is a button the pilot will press, and what it will do, it will come up with the information. Okay, so when he presses this button on this page here, it will tell him the procedure to follow for that failure. Okay, so it could be a hydraulic system failure. It will tell him, the pilot will press a button and it will tell him what to do in the event of a hydraulic failure. In the olden days, the pilots used to get a set of cards out. Okay, and if you look down the right hand side, you've got cards here that's got all in red. Okay, and they'd come up, they'd pick up the emergency and go, right, I've got a hydraulic failure, and he'd follow the procedure. Nowadays, it's all done for him. Okay, doesn't have to go and look at the cards. It's all done for him. Okay, so you're happy on 3 and 4?
Yeah.
Good. We now look at this electronic flight instrument. As we said earlier, we break it down to 1, 2, and 3, pilot, 4, 5, and 6, co-pilot. And they're controlled by something called a DEU, a display electronics unit. Okay, a display electronics unit. What does that do? Okay, those who've got computers, laptops and that, have you ever heard of a VGA card, the graphics card? Yeah, it makes the picture. Well, basically, this is a graphics card. So there's a program in there, and with the program, it's going to look at all the systems it's been designed to provide a picture for. Okay. So the display electronics unit is going to take all this information from the systems. So in like DU1 and 6, it's going to have my vertical gyro. It's going to have airspeed. It's going to have vertical speed. It's going to have rate of climb. Yep. And then my display unit 2 and 5, it will be my compass systems. And in 3 and 4, it's going to be all my engine systems. So it takes the DEU, the display electronics unit, takes the information from the aircraft systems, whether they are analog or digital. Okay. So if it's got analog systems, so voltages or analogs or pressures, it has to convert them into digital. So also in there, it has a analog to digital converter. But it creates this here, takes all this information and will send it as a picture to these screens, okay? To these screens. So you have to understand what is the purpose of a display electronics unit. It takes information from the aircraft systems, whether analog or digital, and converts them into a picture for your TV screens, okay? So you have to be aware of what a DEU does. So 1 and 3 is controlled by one DEU, 4, 5 and 6 by the other. In reality, gentlemen, there would actually be a third. In most of your aircraft now, there would be a third sitting there waiting to take over if something failed. So redundancy. But even if I've got 3, we could actually say one of those might fail as well. So how it works, okay, in a basic system, if I've only got 2 display alert units or I've only got 2 left, the pilots need to have this information at all times. So let's now say the co-pilot's display electronics unit becomes unserviceable. Okay, if it goes unserviceable, the pilot or the co-pilot isn't going to have any of his navigation or primary flight display. So what happens? So the solid red line, okay, from the pilot's display electronic units is feeding display units 1, 2, and 3. When it fails, so when the co-pilot's display electronics unit fails, the pilots, now it'll always depend on whether it's automatic or manual, depending on the aircraft. The pilot can, or the computer will select to allow display the pilot's display electronics unit to feed the co-pilot's display. Okay, so it's always going to get information to fly. The only downside with that is now the information that's in co-pilot, the pilot's displays is exactly the same. It's in the pilot's display, okay? Because they're all now monitoring coming off the one systems. So what happens in the event of the co-pilot's display electronics failing? The co-pilots will take over. Okay. So it says there, note that both DUs are cross-connected to the other DU in the case of a failure. Okay, let's look at failures in the system. Okay. If you look at this here, this looks like it's display unit number 3. So this is DU3. And we said that is the main pilot's information. Yeah. So that would be number 1 engine. That would be number 2 engine. Okay. Now, how we highlight information failures will depend on what the manufacturer has said has gone wrong, okay? But if I have a red cross across information on a screen, okay, it says there, if flight data in the display unit is invalid, either it's been lost or it's been corrupted, the information is replaced by a red or amber cross. So the first thing, just remember, is if information in a display unit is lost, it's replaced with a cross. Okay. Now it could either be a red cross or an amber cross. If it's a red cross, okay, it says that the pilot must take immediate action, okay, to recover the lost data. Okay, doesn't matter if he's in controlled airspace, he's about to land, he needs to basically do something about it immediately, because the manufacturer has actually programmed this computer that this information is urgently or always required by the flight crew. If it's replaced by an amber cross, the pilots don't have to automatically, go and get the information back. Okay, they can delay recovery of the data. Okay, they can play recovery. So you need to understand the difference between a red cross and a amber cross covering certain data in the aircraft system. Okay. If the DEU has failed, okay, now we have said it would automatically change over or manually change over, but for a fraction of a second, all three screens would have a red cross in front of them. Okay. And if all three screens have a red cross, it indicates that a display electronics unit has failed. Okay. If 3, so 1, 2, and 3, or 4, 5, and 6 all have a red cross over them, it indicates that a display electronics unit has failed. Okay, display electronics unit has failed. And if a screen goes completely blank, it indicates that the power has been lost to the display unit, or the display unit itself has gone unserviceable. Okay, so you need to understand these failures. If there's a red cross on one particular part of the display data, it indicates that that data has been lost, but the pilot must take immediate action to recover that data. If it's an amber cross over lost data, the crew can delay recovery of that data. If there's a red cross across 3 of the display units, either 1, 2, or 3, or 4, 5, and 6, it indicates that a DEU has failed. And if a screen goes completely blank, either have lost power to the screen or the screen has failed itself. Now, when we're looking at this, okay, we've only now got 3 TV screens, where before we had lots and lots of gauges. Okay, lots and lots of gauges. So now we need to think about what would happen if any of the displays were to fail. Okay, any of the displays were to fail. Okay, and what we do is have what's basically called a cascade failure, and we have what's called priority logic. Okay, that will basically keep information that we require being displayed in the cockpit. We'll look at this in a minute, okay? So it says there, if only one display unit were functioning. So let's have a look back to this. Right, we have, let's say, we'll just look at display units 1, 2, and 3, okay? I have primary flight display, navigation display, main engine. Which of these displays do you think is the most important display of those three? Who says number 3? Anyone?
Number 3, sir.
You say number 3, thank you. Who says number 2? And does anyone say number 1? No, no one's saying. Well, let's have a look at it. I am flying in cloud, okay? Imagine I'm flying in cloud around controlled airspace. Let's say either London or New York, or Dubai, one of the big airport centres. And I'm only left with one display. What do I need? My attitude, my up and down, my left and right roll, airspeed, vertical climb, rate of descent, glide slope, and attitude, yeah. So, or would I want my engine information, the power of my N1, my N2, my EGT, or do I want to know my compass information? Which one of those three displays?
One.
PFD.
PFD, yeah, because right now, if I'm in cloud or at night, I'm over London, New York or Dubai, if I don't know my attitude, my airspeed, I could fall out of the sky and crash. So I can actually say this is the most important display, my primary flying display. So let's look at what's the next important display? Navigation or the power coming out of my engines? What do you think? Compass or power coming out of my engines? Somebody say navigation?
Yeah.
Yeah? Yep. Or who says engines? Which of these two displays right now, if I lost the information, is going to put the aircraft at risk? Not knowing. Say again?
It's navigation display.
What happens if my engine starts to overtemp or the vibration goes up or the N1 and the N2 start to drop? What's happening to the engine? I'm losing power on my engine, aren't I?
We die.
Well, yeah, you could die if it's both engines, definitely. But the pilot needs to know his power. Okay. Navigation. Okay, I've got my standby compass, haven't I? If I'm in controlled airspace around Dubai, London or New York, I can contact air traffic control for directions. But air traffic control can't tell me how good my engines are. So the next important display is the main engine display, which basically means the navigation is the third most important. Now, so that is the priority that we have. We must have a primary flying display. So if I only got one screen left, if I've only got one screen left, it will always be the primary flying display. Okay? Because you think about it, yes, I want my engines, but if I've got to come into an airport, I need to know I'm going to land, I need to know my attitude, I need to know my airspeed so I don't stall. So if only one display unit is failing, and it doesn't matter whether it's 1 to 6, could be number 4, for instance, it will always be the primary flying display. If I have 2 displays operating, It will be primary flying display and main engine information. Okay, so if I only ever have one display left, I'll always be primary flying display. If I've got two displays, it'll be primary flying display and main engine. So just to highlight here that my primary flying display has been taken over by the attitude indicator. And the navigational display took over from the HSI, the horizontal situation indicator. Be aware of the display units 1, 2, 6. 1, 2, 3 is the pilot. DEU. 4, 5, 6 is the co-pilot's DEU. What is the purpose of a display electronics unit? Is to take the information, whether it's analog or digital, and I'll convert it into a picture for the display. If one display electronics unit fails, the other will take over its information. Failures, okay? All happen that if you lose some of the information, you can get a red cross or an amber cross. A red cross will indicate that the pilot must take immediate action. A amber cross will indicate that it can take time to get the information back. A red cross in three of the DEUs, so 1, 2, or 3, have a red cross. It means the DEU has failed. If a display is completely blank, it indicates that the display unit itself has failed. Any questions in the electronic flight instrument system? No. Does anyone want to go through anything we have done today, or on Friday, or on Thursday? Okay. I know what's it. So it's now 5 1/4. So it's 4. So I take it that's 9 o'clock at night back in Nepal.
Yes.
Is that correct? Right. I know it's getting close to your bedtime. Okay. That's us finished this book. Okay. If you want to stay up, there's the questions in that sheet I gave you. Might be worthwhile going through. I'm going to be here, okay, for over another hour. If you want to ask me questions, please ask me the questions. I'm not going to close down the Teams meeting for another hour. So if you want to read through your notes and you have a problem, you can come back in, ask me a question. I will be here to answer it. So does anyone want to go through any questions? Yes.
The questions you have provided for the practice one.
Yes.
And that there is some MAC number. So
don't worry about that, because the EASA took the requirement. I forgot to take this out. EASA took the requirements 2 years ago for MAC meter to be studied. So basically, ignore the MAC meter. I just haven't taken this out. Okay. So questions. Uh, 62 to 73 you don't need to do, because that's been taken out the syllabus 2 years ago. Okay, so you don't have to do it anymore. Don't know why, because we've got MAC meters in the aircraft, but there you go. So anyone want to, so you don't have to do those questions. Anyone want to go through anything else? No. Right. I know it's 9 o'clock at night. Some of you might be wanting to go to bed. But again, tomorrow when you get up in the morning, have a read through your notes. If you get any questions, ask me. Now, tomorrow you will need the avionics notes, okay, the basic avionics notes. So you can make sure you've got them with you tomorrow. Okay, anyone get any questions? Sorry.
Yeah, the questions you have provided was only for the pitot static and some, I think, of the next chapter. So please give for till today questions.
Yeah, so basically the only questions you don't have to do are 62 to 73. The rest of them, the questions are valid for
compass only, I think.
Yeah, what we have covered in the last couple of days. That's me. I'm not going to start the new book today because it's just there's no point in the time. So either read through your notes, answer some questions, or go and get some sleep. Okay.
Yeah, I'm asking if there is some more questions, then please forward to Yadav.
I have got some more questions. I can do that. Yes, I can do that to Yadav tonight.
Okay.
Okay. So if you give me a few minutes, Yadav, I will email you some more questions. Okay, you happy with that, Yadav?
Yes.
Okay. So, anyone got any more questions for me?
And can we pass with those questions and your these studies?
You need to study. Just doing the questions you won't pass. But doing the questions will help you find the information in the notes. And when you go looking for the information in the notes, you end up reading and you remember things. Okay? So you just won't pass by doing the questions, but the questions will help you to find the information. And that will help you pass. Okay, so I will email Yadav some more questions when I find them. Okay, so I've finished with you on this book. Please make sure you've got the avionics notes tomorrow. Okay, so last chance, anything for me? No. Right, so I'll go and make an email and I'll send some information to Yadav. Okay?
Okay.
Yadav, are you still there?
Yes, I am here.
Could you, can't find, could you send your email address again, please? In the chat. Or you can send it to my email if you want, either way.
Please have it from chat.
Yeah, chat will do fine, yeah. Oh, got it, thank you very much.
All right.
That's why I couldn't find it. I was trying to start it with a Y. Okay, Yadav, that's them new other sheets on the way to you.
Yeah, I have got your mail.
Okay, so if you can pass them amongst the rest of the boys.
Yes, sure, I will.
Thank you very much. Yes.
The questions are only the revision type, or we have some objective questions also to practice.
I've sent some to Yadav.
Okay. Okay, then I will check.
I've just said Yadav should be sending you an email soon with other questions. Okay. So I've finished with you today. You do the questions now or you do them at tomorrow, okay? But I'm going to be sitting here for the next hour. If anyone's got any questions about any of the systems we've been through, wants to go through it again, please let me know. Ben, have you got a question?
Yeah, Mr. In, I have forwarded them.
Okay, what's the question?
The one you emailed us.
Yeah. So what question have you got problems with?
No, I mean I have got the email. There is no
All right.
question for
Okay.
you.
Yes. Fine. Yeah, sorry. Okay. I thought you'd come back in because you had a question. Okay.
No.
No. Okay. You don't have to stay logged in. If you want to go, I'm happy for you to go. If you want to stay, read through the question. If you want to stay and ask the questions, that's fine by me. I'm going to be here as well, so don't worry about it. If you want to stay logged in, please stay logged in.